Welcome to Domain 2 of the Security Plus Exam Cram series, which focuses on architecture and design. And in this session, we're going to touch on every topic in Domain 2 as detailed in the official exam syllabus. And again, this series is designed to help you ramp up quickly by focusing on the key aspects of topics that will help you drill down and choose the correct answers more effectively on exam day. And again, intended to be the first resource you use in your prep to identify your weak spots, and the last resource you review as a refresher before walking into the exam. I'm glad you're here. We have a lot to cover, so let's get started. Welcome to Domain 2 of my Comptia Security Plus Exam Cram series. Today we're covering Domain 2, which is Architecture and Design, so Domain 2 of 5. In the series we have 6 core videos, the first video being the introduction that covers my exam preparation strategy recommendations. I will likely release 5 to 10 shorter supplemental videos, just some drill downs on areas that over time may present themselves as being particularly challenging. So let's get right into it here, and do know that in Domain 2, as in all domains that I'm covering in this series, I will be covering all of the topics in the official Security Plus exam objectives. You will find a link to that document in the video description. And to optimize your preparation and minimize your spend, I recommend the official Security Plus Exam Study Guide and Practice Test Bundle. It has 1,000 flashcards, 1,000 practice questions, a couple of practice exams, and you can get a copy out on Amazon.com for less than $60. I have a link to the least expensive option in the video description. And by the way, it includes a 10% exam discount coupon, which at this point in time in US dollars is going to reduce your cost on the guide by half or better. And as with all of my exam preparation videos, you'll find a PDF copy of the presentation I have here available in the video description. In 2.1, we'll be focusing on the importance of security concepts in an enterprise environment. So for our purposes, enterprise means a large and complex environment. So let's start with configuration and change management. Now, configuration management is really the focus of the exam. I want to just call attention to change management for a moment for its complementary role in supporting configuration management. So configuration management ensures that systems are configured in a similar fashion and that the configurations are known and documented. And baselining ensures that systems are deployed with a common baseline or starting point. And imaging is a common way to achieve this. Infrastructure as code is another way this is achieved, concept we'll touch on a bit later. And change management is a process that helps reduce outages or weaken security from unauthorized changes. And versioning uses labeling or numbering to track changes in updated versions of software or environments. But change management requires changes to be requested, approved, tested, and documented. So even if we have a solid configuration management strategy, if we're allowing unauthorized changes to sneak in, it's going to cause our systems and applications to drift from their baseline configuration. The point being, configuration management can prevent security-related incidents and outages, and configuration supported by change management will do an even better job. Now let's talk through a few basic concepts of configuration management that are called out on the exam objectives. So we have diagrams, which are essentially a picture that show the relationship of all the interconnected devices and components, and ensuring the security team have visibility into the security in place. Standard naming conventions can be helpful, making identifying device types like routers, servers, and printers easier. Oftentimes we see naming prefixes like RTR for router, SVR for server, etc. But whatever the prefix is you prefer, it's really about establishing a standard that works for your team. Asset management, so maintaining an up-to-date asset register to ease the process of tracking and maintaining assets. This allows us to scan for unknown devices and to ensure that devices are patched. Baseline configurations. It's absolutely vital that each type of device is being placed on the network with a secure baseline configuration. Again, image-based deployment helps here, and infrastructure as code is another common practice. Firewall rules. Firewalls can be used to block traffic, and we can use either a mobile device management solution or group policy to change the configuration on the endpoint devices themselves, at least in the case where perhaps we have some sort of client-based firewall. But we want to standardize and automate configuration. And with firewalls, a lot of times, especially in environments where firewalls are virtual appliances, we'll see infrastructure as code come into play. Again, we're going to talk about that later in this lesson. So continuing down the road of configuration management, mobile device management. So an MDM solution can be used to push configuration changes to mobile devices. For example, we might want to require a minimum iOS or Android version, a 6-digit PIN for our phones. We might want to block jailbroken or rooted devices and to manage the applications that are allowed to access our corporate data. Content filters or URL filters. These are blocking harmful content with filtering appliances like a unified threat management appliance or next generation firewalls. UTM actually bundles features like all of the filtering for URLs, emails, antivirus, IPS. That tends to be more of an SMB, a small to medium business scenario. Next generation firewalls use threat intelligence feeds. We see those definitely in the enterprise. Updating or revoking certificates. So certificates facilitate authentication and secure connectivity like TLS, HTTPS, so secure web traffic, and IPsec, VPN connectivity. So we have to track certificate expiration and ensure minimum TLS version support. And that's top of mind in 2021 and 2022 because we've seen TLS version requirements upped in the last few months. IP schema, using network segmentation to reduce broadcast traffic and to enable filtering or restricting traffic to subnets that contain sensitive resources like our databases that might have sensitive corporate data. Matching resources to specific segments is going to maximize data and resource security. So we can use subnetting and port filtering in this case. And then there's data sovereignty, which speaks to the reality that digital data is subject to the laws and regulations of the country in which it was created. You can't move data into another region, even for backup-related reasons. And data is subject to the laws of where it is stored, which can have very significant legal implications. The reality is, a company's legal department should be consulted to offer guidance on the legal impact of geography on data sovereignty. And moving data out of the European Union doesn't remove GDPR requirements. GDPR really speaks to where the customer is located, the user is located. So if you have customers or users in the EU, then GDPR applies to your business regardless of where your business may be located. So data protection. So confidentiality is often protected through encryption, both at rest and in transport. And we're going to talk about cryptography in section 2.8 of this lesson and in some select areas beyond domain 2 of this series. So moving on, tokenization is where meaningful data is replaced with a token that's generated randomly and the original data is held in a vault. It's stateless and it's stronger than encryption. The keys are not local. And then we have pseudo-anonymization, where we're de-identifying personally identifiable fields within a data record. They're replaced by one or more artificial identifiers or pseudonyms. So reversal actually requires access to another data source, but the key there are the artificial identifiers or pseudonyms. So data masking. This is when only partial data is left in a data field. For example, a credit card may be shown with only the last 4 digits. I expect you've seen that if you've ever made a purchase online. You'll see similar masking with your social security number or social identity, depending on where you live. It's commonly implemented within the database tier, but it's also possible in code on front-end applications. So in data loss prevention, or DLP, as you'll often hear it referred to, this is a way to protect sensitive information and to prevent its inadvertent disclosure. So most of your DLP systems can identify, monitor, and often automatically protect sensitive information in documents. And DLP reports showing content that matches the organization's DLP policies will generally be available. But policies can typically be applied to email, to your SharePoint collaboration sites, to cloud storage, and to, in some cases, even to databases. So you may see questions on the exam related to protecting data at rest. So how can we encrypt different types of data at rest? Well, we have storage service encryption, and your CISSP storage providers, your cloud service providers, usually protect data at rest automatically by encrypting before persisting it to managed disks, to blob file, or queue storage. Takeaway here is the CSPs are usually encrypting at least at the service level by default, and that's in no small part due to some of the early challenges cloud providers had in open permissions resulting in unwanted data disclosures. We have full disk encryption, which helps you encrypt Windows and Linux IaaS VMs or even physical endpoints, both their OS and data disks, using BitLocker on the Windows platform and the DMCrypt feature of Linux. And for our databases, we have transparent data encryption, which helps protect SQL databases and data warehouses against the threat of malicious activity with real-time encryption and decryption of database backups and log files at rest without requiring application changes. So digging into protecting data at rest a little further, let's talk about full disk encryption under the hood. So your endpoints have a trusted platform module. It's on the motherboard. It's used to store encryption keys, so when the system boots, it can compare keys and ensure that the system hasn't been tampered with. So it's generally speaking an element of hardware. But there's a hardware root of trust. So when using certificates for full disk encryption, they use a hardware root of trust that verifies that the keys match before the secure boot process takes place. And then there are self-encrypting drives. There's the Opal storage specification, which is really industry standard for self-encrypting drives. It's a hardware solution, and it typically outperforms its software-based alternatives. Now, they don't have the same vulnerabilities as software, really, so they're going to be more secure, fundamentally speaking. And these self-encrypting drives are usually solid-state drives, and they're purchased already set to encrypt data at rest. The encryption keys are stored on the hard drive controller, but they're essentially immune to a cold boot attack, and they're compatible really with all operating systems. Self-encrypting drives are effective in protecting the data on lost or stolen devices like a laptop because only the user and the vendor can decrypt the data. We also need to be familiar with how to protect data in motion. So how do we encrypt data in motion? Well, most often data in motion is encrypted using transport layer security, TLS, or HTTPS, as you'll hear it referred to. And this is typically encrypting a session before a user enters sensitive details like credit card information. Now, while that's similar in functionality to SSL, TLS has largely replaced SSL in the last few years. And data in use, or sometimes called data in processing. This occurs when we launch an application like Microsoft Word or Adobe Acrobat. An app's not running the data from the disk drive, but they're running the application from memory, typically. This is volatile memory, which means that should you power down the computer, the contents will be erased. But sometimes you'll hear data in use called data in processing, so just two ways of saying the same thing. It's pretty common that you'll be faced with protecting secrets as well. So a secret is anything that you want to tightly control access to, like API keys, passwords, certificates, tokens, or cryptographic keys. Now, password access management solutions, or PAM solutions, offer centralized secure storage and access for application secrets. And enterprise solutions typically offer policy-based access controls and programmatic access to secrets, such as through an API. This is going to be a really common component in DevOps or DevSecOps scenarios. Now, digital rights management, or DRM, we hear a little less about today than we used to in years past. But DRM allows content owners to enforce restrictions on the use of their content by others. It commonly protects entertainment and media content like music, movies, and ebooks. That's really where you'll hear about DRM today. Occasionally it's found in the enterprise protecting sensitive information stored in documents, but you'll hear about it much less in that context. Now, in the enterprise scenario, you'll hear about Information Rights Management, or IRM. So IRM programs enforce three things: data rights, provisioning access, and implementing access control models. As an example, Microsoft's IRM provides policy-based control over data and can be used to block specific actions like print, copy, paste, download, and sharing, and offers file expiration so that documents can no longer be viewed after a specified time. This is a space that's evolving all the time, and Microsoft and other vendors offer multiple avenues for protecting data. But that first line there, data rights, provisioning access, and implementing access control models, is the core functionality of IRM. Let's talk about geographic considerations for a moment, for data, for systems, services, and personnel. So in terms of distance, while the fastest site to restore services is a hot site, a site hundreds of miles away is going to be impractical or inconvenient in some respects, although it may be necessary. So selecting a location of the hot site is going to be critical to the speed of data, systems, and service recovery. Now, considerations for personnel may vary. If we need to get staff back online quickly in the event of a disaster, they're not going to be able to travel hundreds of miles away, so the location selection for our data systems and services may be different than location selection for personnel. But it should be far enough away to ensure that our services can be recovered in the event of a natural disaster like a hurricane or a tornado. Now, offsite backups, when we back up our data, physical backup media like tapes should be stored in a fireproof safe offsite. And similarly, disk-based backup should be stored offsite in a cloud or other secure remote repository. Cloud services are a common solution for this today. That being said, let's talk about how cloud service providers handle site failover. And I'm going to talk generically here in the context of large providers like Microsoft, like Amazon, and Google. So we have geographies, and a geography represents a discrete market, typically containing two or more regions that preserves data residency and compliance boundaries. But you'll see the largest providers have geographies all around the world. And then within those geographies, they have regions. So regions are a set of data centers deployed within a low latency defined perimeter and connected through a regional low latency network, a dedicated network to be sure. And within those regions, they have region pairs. So this is a relationship between two regions with the same geographic region for disaster recovery purposes. And you'll see a relationship between these two as a primary and a failover, typically chosen by the cloud service provider. Often you as a customer don't get to choose those pairs, and the pairs are generally separated by 300 or more miles. And the reason you don't get to choose those pairs, number one, it allows the CISSP to ensure that a good decision is made here that will allow that failover to happen to another data center with enough distance to ensure that we don't have two primary and secondary data centers affected by the same disaster. But also it allows the cloud service provider to pre-configure failover at a service level, such as for storage and network connectivity and data replication potentially. So if you've configured a redundant tier for storage, you'll find failover is automatic. If you've configured data replication for, say, a SQL solution in the cloud, a PaaS service, typically that failover is going to be possible automatically. And exactly how this works might vary a bit by cloud provider, but they're all going to have a similar strategy at the highest level. You may see questions on the exam around response and recovery controls, and there are three types of incident response plans you should be familiar with for the exam. So there's the read-through test, where you distribute copies of the incident response plans to the members of the incident response team for review. The team members are going to basically read through and provide feedback about any updates needed to keep the plan current. We then have a structured walkthrough, also called a tabletop exercise. This is where members of the disaster recovery team gather in a large conference room and they role play a disaster scenario. Usually, the exact scenario is only known to the test moderator, who presents the details to the team at the meeting, so nobody knows exactly what's going to happen until they walk in the room. The team members refer to the document and discuss the appropriate responses to that particular type of disaster. Now, what these two incident response options have is these exercises are all talk at this point. Now, the third type of incident response plan to be familiar with is the simulation test. This is similar to a structured walkthrough, except some of the response measures are then tested on non-critical functions. This one involves some form of doing, and that's the major difference of the simulation test. And enterprises really need these controls to minimize service interruption and to coordinate recovery at scale with appropriate security, whether it's a security incident or some other type of disaster. So securing traffic. So for email, standards for encrypted messages would include SMIME and pretty good privacy. For web, the de facto standard is going to be TLS, Transport Layer Security, so HTTP over Transport Layer Security, which is HTTPS, which largely replaces SSL as mentioned previously. And then at the network layer, the IPsec protocol standard provides a common framework for encrypting network traffic. It's really built into many common operating systems and a component supported by many network hardware providers. So I want to talk about hashing for just a moment, and hashing versus encryption. So it's important that you know the difference. So encryption is a two-way function. What is encrypted can be decrypted with the proper key. Hashing, on the other hand, is a one-way function that scrambles plain text to produce a unique message digest. So for example, if you were to look at passwords in memory on a system, your passwords are typically hashed, and it's the password hash that's passed between systems in an authentication sequence. So there's no way to reverse a hash if it's properly designed. So good hash functions have 5 requirements. I don't think you need to know these specifically for the exam, but it's going to be useful for your understanding of hash functions. So they have to allow an input of any length. They need to provide fixed length output, which means no matter what the length of the input was, the output's going to be the same length. They need to make it relatively easy to compute the hash function for any input. They need to provide that one-way functionality. What is hashed cannot be reversed. And they must be collision-free, which is why you won't see some protocols used today that were used previously for hashing, because they are prone to collisions. That's why MD5 is much less common today than it used to be, because it is collision prone in some circumstances. And a bit later in this lesson, we'll talk about how hashing and the different types of encryption are used together, how they complement one another. So let's talk about application programming interfaces, or APIs. So SOAP and REST are the two common standards out there. REST is the modern standard, but an API is a set of exposed interfaces that allows programmatic interaction between services. Now, REST uses the HTTPS protocol for communications to offer those API endpoints. Security mechanisms will include API gateways, authentication, IP filtering, throttling, so throttling the max number of requests that can come through in a given time. Oftentimes, commercial APIs will have a quota. You can consume a certain number of requests over a given period of time. And data validation, of course, is always going to be important. Now, we also need to ensure that storage, distribution, and transmission of API access keys is performed in a secure fashion. That access key is essentially a secret. So there are 3 primary types of recovery sites that you should be familiar with for the exam, and that would be hot, warm, and cold sites. So let's start with cold sites. So a cold site is essentially just a data center space, power, and network connectivity that's ready and waiting whenever you might need it. To recover, if a disaster strikes, your engineering and logistical support teams can readily help you move your hardware into the data center and get you back up and running. So the cost of a cold site is going to be relatively low versus the other site types, but the effort to get it up and running is going to be high. Now we have warm sites. So the warm site is a preventative measure that allows you to pre-install your hardware and pre-configure your bandwidth needs, generally speaking. To recover, if you have an incident, all you have to do is load your software and data to restore your business system. So the cost here is going to be medium. The effort to recover will also be medium relative to the other types of recovery sites. And then we have the hot site. A hot site is proactive. It allows you to keep your servers, systems, and a live backup site up and running in the event of a disaster. You can essentially replicate your production environment in that data center. And then to recover, you're basically looking at an immediate cutover in the case of a disaster at your primary site. A hot site is going to be a must for mission-critical sites and services. The cost is going to be high, but the recovery effort is going to be low because you have really a live site up and running. Oftentimes you're replicating data in near real time over to that hot site. To finish up section 2.1, we're going to talk about methods of deception and disruption, so how we can disrupt and deceive our attackers. So there's the honeypot that basically allows us to lure bad people into doing bad things and allows us to watch them. Now, we are only intending to entice our attackers, not to entrap. In other words, you're not allowed to let them download items with enticement. For example, allowing an attacker to download a fake payroll file to actually commit a crime would be entrapment, and at least in the context of U.S. law. The goal is to distract from real assets and to isolate them in a padded cell until you can track them down. A group of honeypots, incidentally, is called a honey net. But a honeypot is a system that often has pseudo-flaws and fake data to lure intruders in. It lures and distracts attackers from our real resources. As long as the attackers are in the honeypot, they're not in the live network, disrupting our production services, and our admins can observe. And some intrusion detection and prevention systems actually have the ability to transfer attackers into a padded cell after detection. A padded cell is essentially a simulated environment that might offer fake data just to retain an intruder's interest. We have the honey file, which is a decoy file, deceptively named, so it attracts the attacker's attention. And then fake telemetry, so when security teams send false information back to an attacker spotted using offensive security tools like port scanners, we call that fake telemetry. But a honeypot can be used to examine the attack methods that attackers use to help direct the fake telemetry response. And finally, we have the DNS sinkhole. So we can create a DNS blacklist on a firewall that can identify malicious traffic trying to gain access to our network. And the sinkhole protects users by intercepting DNS requests attempting to connect to known malicious domains and returning a false or what we call a controlled address. And that controlled address can point to a sinkhole server in a honeypot. But notice how the tools in this section work together. So the sinkhole, the honeypot, the honeynet, etc. are complementary. So we have layers. So moving on to section 2.2, summarize virtualization and cloud computing concepts. So we'll talk about cloud models, we'll talk about the advantages of on-premises and off-premises, infrastructure as code, serverless architecture. Summarize in this context means explain. So you really just need to be conversant on these topics. We'll start off with cloud models and services, and I'd like to explain these to you in the context of the shared responsibility model. So when you're running on-premises, security for the entire stack, all the way down to the wire, the physical data center is 100% yours. You own it as the customer. Now, when we move into the cloud, we're handing over some responsibility to the cloud service provider. So in the IaaS model, infrastructure as a service, think virtual machines, we're handing over control, some responsibility for networking, storage, servers, and virtualization. So the hypervisor, we don't have to worry about that anymore. We're really dealing with the virtual machines. In the platform as a service model, we're handing over more control and now the CSP is handling the OS, the middleware, the runtime. We're really just worried about our data and the applications we're running in the PaaS context. And when we get into a software as a service model, we're really handing almost all the control over to the cloud service provider. So in a SaaS scenario like Office 365, we just have limited responsibility for the applications and the data, really just access control to the applications and fast recovery of our data, even though there's going to be some protection there with the CSP. But you notice that in terms of responsibility, as we move from on-premises over to SaaS, we're handing over increasing levels of responsibility to that cloud service provider. So let's just look at some examples here. So for IaaS, the CSP provides the building blocks like networking, storage, and compute. The CSP manages the staff, the hardware, the data center. Some examples here would be Azure Virtual Machines, Amazon EC2, Google Cloud Platform, Compute Engine. So these are all really virtual machine solutions branded in those CSPs. So platform as a service, customers responsible for deployment and management of apps. The CSP manages provisioning, configuration, hardware, and OS, in addition to everything they're managing that we mentioned in the IaaS model. Some examples here would be database as a service, API management, Azure App Service, for example, is web apps, so Amazon and Google will have similar offerings. Then software as a service, as a customer, we just configure the features. You have to configure your access control, so who has access to the features within the SaaS, and then you'll have some responsibility for data. So for example, in the Office 365 context, you'll see customers purchase a third-party backup solution to back up their Office 365 data to the cloud for faster recovery. But the CSP is responsible for management, operation, and availability of the service. So we just have that limited responsibility for access management and data recovery. Some examples of SaaS applications include Office 365, ServiceNow, and Salesforce. All right, moving on, let's talk about the benefits of cloud computing and the differences between some of the cloud models. So the cloud is cost-effective, it's global, it's secure, it's scalable, it's elastic, and it's always current. So there's much less effort for a customer to stay up to date and to ensure that they have the ability to scale and to be elastic in terms of responding to spikes in demand. So the public cloud, where everything runs on our cloud provider's hardware. So public cloud would be moving everything into the cloud. We don't have anything in our data center. But the public cloud refers to Azure, Amazon, Google Cloud. Advantages here include scalability, agility, pay as you go. That's what PAYG means. There's really no maintenance. The skill requirement when moving into the cloud is lower because all of those advanced infrastructure, the scale, the availability, the networking, that's handled for us by the cloud service provider, as is a lot of the underlying security for all of those elements. So private cloud, that's a cloud environment in your own data center. So the advantages of a private cloud include legacy support. So if we have legacy applications or infrastructure that need to run for an extended period of time, maybe even beyond their mainstream support, it's our perspective to do that. We also have full control over the environment, which means in compliance scenarios, we have full control for configuring compliance. Whereas when you move into the public cloud, in some cases you will be constrained by the limits of the services provided by that cloud service provider. So a hybrid cloud combines public and private clouds, allowing you to run your applications in the right location. And this is the flavor of cloud computing that most enterprises use today. They'll run many applications and services in the public cloud, but for some of those legacy scenarios, some of those scenarios that require specific aspects of control and compliance, they'll run those in their private data center. And sometimes that's really just a matter of running hybrid to allow for time to move applications to the public cloud. But hybrid is really where most enterprises are today. But it gives us flexibility in those legacy, compliance, and scalability scenarios. We can choose the right location for running different services. A couple of other terms to be familiar with. There's the XaaS acronym, Anything as a Service, which describes the range of other cloud as a service offerings, whether that's desktop as a service, backup as a service, or any other as a service offerings that appear. I see this term pop up less frequently in the real world, to be honest. Community cloud. So this is a collaborative effort in which infrastructure is shared between several organizations, usually from a specific community with common concerns around security and compliance. For example, you might see several law firms, for example, running in a community cloud, or maybe particular niche health organizations. And that community cloud may be managed by its members, or it could be managed by a third party, but it's just a collaborative effort to produce efficiencies for organizations with common requirements. So the cloud service provider, which I've mentioned several times today, these are entities that resell cloud services to customers. Azure, Amazon, Google Cloud, Oracle, IBM are all CSPs. They might provide infrastructure, software, VMs, and other services. The IaaS, PaaS, and SaaS models that we talked about, they may provide day-to-day management for some types of services, and most of them do. What they provide varies by your needs and the plans you choose. So a managed security service provider maintains a security environment for companies. They may manage firewalls, intrusion detection and prevention systems, SIEM systems, and other security services and infrastructure. And they may provide outsourced security operations, a security operations center, and incident response services, essentially providing you that skilled security staff. And touching briefly, just to summarize on-premises and off-premises, so cloud versus on-premises hosting. So on-premises servers are the traditional enterprise computing model. The business buys and maintains its own servers, network, storage, etc., located in a secure climate-controlled room, typically on-site or near-site in a dedicated data center. Moving to cloud shifts some responsibilities to that cloud service provider. What it also does is shifts IT spending from capital expense, so investment in infrastructure and servers, etc., to operational expense, to that pay-as-you-go model where you're just paying for what you consume. So know the advantages of cloud and on-premises for the exam, which we covered in the cloud models content in this video just a moment ago. Edge computing. So some compute operations require processing activities to occur locally, far from the cloud, essentially. So common in various Internet of Things scenarios like agricultural or science and space or military, you'll see that need to perform some compute near the devices at the edge rather than pumping that data all the way back to the cloud for processing and then sending it all the way back down to the edge. But all the processing of data storage is closer to the sensors rather than in the cloud data center is the point. So with large network-connected device counts in varied locations, data encryption, spoofing protection, and authentication are going to be key to ensure that all of the devices in the scenario, in these IoT scenarios, are secure and authentic and not compromised. Next up, we have fog computing, which complements cloud computing by processing data from IoT devices. Fog computing often places gateway devices in the field to collect and correlate data centrally, but at the edge, so near the devices far from the cloud. Generally, this brings cloud computing nearer to the sensor to process data closer to the device, but in a centralized or aggregated fashion. So perhaps there's a gateway for all devices in a specific geography or region, for example. So it's important in this case to speed processing time and reduce dependence on cloud or internet connectivity in mission critical situations. This is common in healthcare, for example, where you have human life at stake and processing time may be paramount. And the lack of availability of the cloud for any reason for a limited period of time could, cause a unique danger in that scenario. Next up, we have the thin client. So The thin client is a client-side concept where the client has limited resources that are insufficient to run applications locally. It connects to a server and it processes an application on the server's resources. This may be a purpose-built device, and often thin clients are, or it could be a PC that's just running specific client software that allows it to be multi-purposed as a thin client. So it can function as a PC and also leverage that thin client capability. You'll see thin clients used commonly in call centers to reduce cost and complexity and replacement time for large numbers of users. If you have a thin client go down, replacing that thin client is pretty simple because they tend to be fairly simple devices relative to a full PC, which has a lot more running locally. Containerization. So containers are a lightweight, granular, and portable way to package applications for multiple platforms. It's going to reduce overhead of server virtualization, which are virtual machines, by enabling containerized apps to run on a shared OS kernel. And that is to say, containers don't have their own operating system. They're smaller boundaries that don't have their own OS. They're sharing that kernel, although the container may believe it has its own kernel based on the container architecture, the platform it runs on. Containerization shares many of the same concerns as server virtualization, so isolation at the host level, the process level, the network level, and the storage level, and how you go about that in the container world is different than virtual machines. It takes specialized skills for sure. It can be used in cases to isolate existing applications developed to run in a virtual machine with a dedicated operating system. There are apps that we see ported successfully from a VM environment to a container environment without a dedicated operating system any longer. Docker and Kubernetes are the two most common examples that come to mind of container platforms. You shouldn't need to worry too much about those details for the exam. It's really just the concept you need to focus on here. So microservices and SOA, or service-oriented architecture. So SOA is creation of discrete services that may be accessed by users in a black box fashion. You don't know exactly what you're dealing with. Microservices are fine-grained services with a discrete function. It's really a modern adaptation of service-oriented architecture to cloud computing. In this scenario, code-level vulnerabilities should be identified early in the development lifecycle. Really what we see commonly is static code analysis and dynamic testing are incorporated early in the CI/CD process to identify deficiencies before they're released to production. We're going to touch on what exactly CI/CD is in just a moment, so stick with me. So we mentioned APIs earlier, so this is a set of exposed interfaces that allow programmatic interaction between services. REST, the most common API today, the most common standard today, uses HTTPS to secure communications. But APIs are loosely coupled and can be reused when creating applications. And in fact, that was a standard set by Amazon pretty early in their existence. When one business unit created a service, they would have to make it available to other business units as an API so they could consume whatever was developed as a service. Cloud service providers offer multiple security controls for APIs that we mentioned briefly back in section 2.1. And sometimes for APIs, you'll see third parties that add on to cloud service providers to add some additional accounting features, which enable granular usage tracking per user and potentially chargeback capability. So next up is infrastructure as code. So this is the management of infrastructure, generally virtual infrastructure, networks, VMs, load balancers, and connection topology described in code. Now, just the same as source code generates the same binary, code in the infrastructure as code model results in the same environment every time it's applied. And infrastructure as code is really a key DevOps practice, and it's used in conjunction with continuous integration and continuous delivery called CI/CD. That's where checking code into the repository kicks off a process that will then potentially compile code, deploy that into a test environment where it can be tested, scanned, tested dynamically or statically, and then moved on to a staging environment before it finally moves into production. Infrastructure as code is very common. It's really the standard in cloud computing. Software-defined network. So SDN is a network architecture approach that enables the network to be intelligently and centrally controlled or programmed using software, and has capacity to reprogram the data plane at any time. Use cases for this include SD-LAN and SD-WAN, so software-defined local area and wide area network. But it's basically separating the control plane from the data plane, and it opens up a number of security challenges. So SDN vulnerabilities can include man-in-the-middle attack and denial of service, and you'll secure software-defined networks with TLS, generally speaking. So another concept in the software-defined realm is software-defined visibility, which provides visibility of the network traffic use. It can collect and aggregate network traffic data and provide better reports to the network admins. It might extend the capabilities of a platform so it can programmatically tie together security tools, but it can increase the effectiveness of multi-tiered security architecture in stopping data loss and theft. It's providing a more complete picture to the team responsible for network and data security. Then there's serverless architecture. So this is a cloud computing execution model where the cloud provider dynamically manages the allocation and provisioning of servers and resources. It's hosted as a pay-as-you-go model based on use. The resources are generally stateless, the servers are ephemeral, and they're often capable of being triggered, so basically laying idle and triggered when they are needed for use. A really common example of serverless architecture is function as a service, and most of your major cloud service providers offer some form of function as a service where we can have a piece of code that can be called to execute and potentially process data as we need it to. Then there's services integration. So this is provisioning of multiple business services combined with different IT services to provide a single business solution. So bringing the services together with the human element to provide a single solution. So combining technology with IT services, oftentimes from a third party. So I do want to talk about how serverless is different from platform as a service in terms of responsibility. I don't know what you'll face exactly on the exam in 2022, but I want to call out the difference between serverless and platform as a service because there's oftentimes confusion in this area. So what platform as a service and serverless have in common is devs do have to write code and there's no server management. In the shared responsibility model, that's been handed off to the cloud service provider. But with platform as a service, we have more control over the deployment environment. In the serverless context, we typically have less control. So you'll see websites hosted on platform as a service, and serverless is where you'll see function as a service come up. In the PaaS world, the application has to be configured to auto-scale. In the serverless context, the application generally scales automatically. I mentioned in serverless, the resources are stateless, the servers are ephemeral. They're being scaled automatically in that respect. In platform as a service, the application takes a while to spin up typically. In serverless, application code only executes when invoked. Remember, I mentioned it could be triggered. That means in the serverless context, it sits idle until it's called, which would make pretty good sense when we're thinking about a web site that when we bring it up, it takes a while to spin up, where a function is a bit of code that lays there until it's called to execute and potentially process data. Now, resource policies are another area we see come up in cloud computing, and these policies state what level of access someone has to data or a particular resource. Most cloud service providers have solutions to automate enforcement of your resource policies. Essentially, you can define your policies as code and apply them to your cloud infrastructure and services in various respects. A transit gateway is a network hub that acts as a regional virtual router to interconnect virtual private clouds and VPN connections. This is often an element of a hybrid cloud where you're connecting your on-premises network over to your cloud subscription. You could also see this sort of transit gateway to connect clouds on different CSPs. So maybe I want to connect my Azure subscription to my AWS subscription. I might have a transit gateway in there that helps me do that. And to round out section 2.2, we're going to touch on some virtualization concepts. So server virtualization is the process of dividing a physical server into multiple unique and isolated virtual servers, or virtual machines we sometimes call them, by means of a software application, specifically a hypervisor. The related concepts in this section in 2.2 indicate that server virtualization was really the intent of that line item. So VM escape is where an attacker gains access to a VM and then attacks either the host machine that holds all the VMs, the hypervisor, or perhaps the other VMs. So protection in this case would be to ensure that patches and the hypervisor and VMs are always up to date and that guest privileges are low. So server level redundancy and host-based intrusion detection and prevention are also going to be effective security mechanisms in this respect. Then there's VM sprawl. This is when unmanaged VMs have been deployed onto your network, and because IT doesn't know it's there, it probably isn't patched, it may not be protected, and thus it's going to over time become more vulnerable to attack. Avoidance in this case would be enforcement of your security policies for adding virtual machines to the network, as well as periodic scanning to identify new virtualization hosts and virtual machines. And really this goes back also to our configuration and change management processes that support this capability. If we have a process for tracking configuration and tracking deployment, then we're going to be able to ensure that its ongoing management and security are looked after. Now we're on to section 2.3, summarize secure application development, deployment, and automation concepts. So what we see there under automation and scripting really speaks to CI/CD, continuous integration and delivery, or continuous integration and continuous deployment, which is really a DevOps discussion and increasingly comes up in DevSecOps discussions. So let's talk about environments. So secure environments for development, testing, and staging before moving an application to production are an absolute necessity. So environments map to the phases of application development, debugging, testing, and release. So we have a development environment where the application is initially coded, often through multiple iterations or versions. And testing, where developers integrate all of their work into a single application. This is where regression testing happens to ensure functionality is as expected. Then we can move to staging, where we ensure quality of the application before rolling it out to production. This is where you may do load or scale testing. There may be some additional security testing here from a user perspective, from the outside. This is where your stakeholders, your users, are going to ensure that the user experience meets their quality assurance bar before approving it for production rollout. But QA happens right there in staging. And then production is where the application goes live and end users at that point have the support of the IT team as it's now a production service. And based on production use of the application or service, we'll then see a feedback sent back to the dev team, and they will potentially iterate into future versions of the application, new services, features, etc., or bug fixes potentially. So let's talk provisioning and deprovisioning. So provisioning is the process of making an application or service available. It may also refer to the life cycle of designing, preparing, creating, and managing the applications. And then deprovisioning occurs when the application meets its end of life. And your applications, when they're no longer needed, should be deprovisioned in accordance with local regulations like HIPAA or GDPR, where there may be specific requirements around retiring that application and the data that it may be hosting. Integrity measurement. So this is measuring and identification of changes to a system away from its expected or baseline value. So this ensures that the application performs as it should and conforms to data industry standards and regulations. So code updates should be regression tested to ensure that functionality is intact and no security vulnerabilities exist. The result is a secure baseline configuration. And this sort of measurement should be performed regularly to ensure that applications and systems have not drifted from their security baseline. This is really going to be an element of ongoing configuration management. And you want to be familiar with some basic secure coding techniques. So secure coding techniques should address conditions that may result in vulnerabilities that can be exploited by attackers in our custom applications. So normalization is a database concept. So each database has a list of tables that are broken down into rows and columns. And in a large relational database, data may be retained in multiple places. There's some duplication. The goal of normalization is to reduce and eliminate redundancy to make fewer indexes per table and make searching faster. And then we have stored procedures. A stored procedure is reusable prepared SQL code, generally transact SQL. So the advantage of a stored procedure is it'll provide the required information while ensuring an attacker will not be able to modify the code it contains. It's pre-compiled, essentially. So obfuscation or camouflage. This is a process of obscuring source code so that if it was stolen, it cannot be interpreted or reverse engineered by the attacker. So XOR and ROT13 algorithms can be used to mask data, and steganography, which we'll touch on a bit later, can be used to hide or camouflage the source code. And then there's the concept of code reuse. When we're developing a new application, a developer may start with previously developed code and then modify it for a new application. And reuse is perfectly good if the code quality is high, if it's high quality secure code. Now, dead code is code that's never executed but may just consume resources and increase attack surface. Dead code should absolutely be removed. You want to know some basics of server-side versus client-side execution and validation. So server-side or back-end refers to your databases and database servers, application servers, domain controllers. Those are all back-end servers. C# and .NET are examples of server-side programming languages, incidentally. Now, client-side or front-end validation happens on the client in the browser. So JavaScript and HTML5 are examples of client-side languages. And memory management is another secure coding technique. Code should be written to minimize memory consumption and return memory to the system when it's no longer needed. Failure to manage memory in code may result in memory leaks, and if exploited by attackers through, say, denial of service attacks or through just excessive requests, they can potentially congest processing by consuming all the memory in a system. So third-party libraries and SDKs are sometimes used in development, and third-party libraries can speed development time, but may provide users with greater access than desired and may come with security vulnerabilities of their own, so these need to be selected and validated carefully. An SDK or software development kit is a software development tool kit that a vendor creates to make application development easier. Data exposure needs to be considered in the application development process, and sensitive data should be encrypted to prevent it from being stolen by attackers and sometimes even masked to the user. Masking is common for credit card and password data or even social security number information. Data allocation to a user should be limited. We should really operate on a least privilege basis there, and we need to protect data through input validation and data protection techniques. So validating form input, for example, can prevent SQL injection attacks. XOR or exclusive OR is something I mentioned just a moment ago as an element of secure coding. We use it to mask, obfuscate, or otherwise camouflage source code so it can't be reverse engineered. And it's used pretty frequently in cryptology. It sounds more complicated than it actually is, but it's really just a function of flipping bits in a simple systematic fashion. If the original value and the key value match, the cipher value is 0. And if the original value and the key value don't match, the cipher value is 1. So OWASP, the Open Web Application Security Project. So this is an organization that provides an up-to-date list of the most recent web application security concerns. Their mission is to improve software security through open source initiatives and community education. Their resources include tools, news and information, community and networking opportunities, as well as education and training. They're a non-profit foundation, which means OWASP relies on donations. You may be familiar with their OWASP Top 10 application vulnerabilities list. And in fact, in the cloud, you'll find web application firewalls that have available to them OWASP top 10 rule sets that will allow you to quickly configure a web app firewall in the cloud to protect against those OWASP concerns like SQL injection attacks, like cross-site scripting, and several others. Software diversity refers to creation of software that's different on each user endpoint or device. One of the common techniques is to include dynamic paths in the compiler at compile time, but the result is a binary that's slightly different on every endpoint, or at least in a different location, and this makes the process of exploiting a software vulnerability more difficult for attackers. It minimizes the attack surface if a vulnerability is discovered because it can't be automatically exploited on every endpoint. Continuous validation is testing to make sure that the application is fit for its purpose, it fulfills the user's requirement, and security requirements are met. Continuous validation, bottom line, ensures that application and system updates do not introduce new security vulnerabilities. So elasticity is a concept that may come up on the exam. So this is the ability of a system to automatically grow and shrink based on application demand. So dynamic scaling in both directions. And then we have scalability, which is the ability of a system to handle growth of users or work. So scalability really speaks to the top-end processing capability of work of an application or a service, where elasticity is really talking about services' ability to dynamically respond to increases or decreases in demand. So version control. So as your software is updated, as updates are released, major and minor version numbers are typically updated. This ensures that newer and older versions of the software can be identified, and it allows the security team to track security vulnerabilities and vendor support. So versions typically factor in vendor support statements. For example, a vendor may tell you they only support the current and X number of previous versions of an application, say perhaps the current version and 2 previous versions. That brings us to section 2.4, summarize authentication and authorization design concepts. So we'll be talking about authentication methods, digging into biometrics, and discussing multi-factor authentication. So let's start with one-time password methods. So we have the HMAC-based one-time password, which uses a key hash message authentication code, or an HMAC, and it relies on 2 pieces of information. A secret, which is only known by the token and the validating server, and the second is a moving factor, which is a counter. It's also abbreviated as HOTP, so HMAC-based one-time password. And then there's a time-based one-time password, it's a TOTP, and it's based on HOTP, but where the moving factor is time instead of the counter. And it usually uses time in increments of 30 to 60 seconds, called a time step. And each one-time password is valid for the duration of the time step. So token key. This is a one-time password provided on hardware or software token generators. So authenticator apps are common software solutions for token keys. Then we have static codes, so a static set of numbers and letters to provide for authentication. A password or passphrase is an example of an alphanumeric static code. Then there's a smart card, which is a credit card size token that contains a certificate used for authentication in conjunction with a PIN. This generally requires physical proximity or insertion into a smart card reader. So you've either got a reader that's proximity based or requires the card to be inserted. Authentication applications, or authenticator apps as they're more commonly known, are software-based authenticators that implement 2-step verification services using the time-based one-time password algorithm and the HMAC-based one-time password algorithm for authenticating users of applications. Examples include Microsoft Authenticator and the Google Authenticator app. So these apps use open standards developed by the Initiative for Open Authentication, or OATH. So you'll hear HMAC and the time-based one-time password tokens called OATH tokens with some of these providers. Then there's push notification. This is where the server is pushing down the authentication information to your mobile device. It uses the mobile device app to be able to receive the pushed message and display the authentication information. Then there are SMS messages. So SMS is used as an additional layer of security where the user is authenticated and an SMS message is sent to the user's mobile phone, typically as a second factor of authentication. You could also use a phone call to perform the same type of function, and instead of having an app, an automated process simply calls your phone. And then you respond with a PIN or other input via voice or the keypad. Now, SMS and phone are less desirable, considered less secure, generally speaking, than authenticator apps and biometrics, because if someone can hijack your SIM card, like walk into a mobile phone store and convince the clerk to provide a replacement, then they can hijack that second factor. Attestation. So one of the conditions to access corporate resources may require the access request originates from an approved managed device. So attestation is the process of confirming the device, whether it's laptop, mobile device, etc., is an approved device compliant with company policies. Remote attestation involves checks that occur on a local device and are reported to a verification server. This would be common with a mobile device management solution like Microsoft Intune or AirWatch. Generally, this includes validation of a unique identifier for the hardware that confirms the device is known. Device attestation is common in zero trust architecture. Directory services. So directory service is used to store, retrieve, and manage information about objects like user accounts, computer accounts, potentially mail accounts, and information on these resources. LDAP is a common protocol for a directory service. It's used by Microsoft Active Directory Domain Services, which is pretty common in the enterprise. Directory services are typically coupled with an authentication service to authenticate entities, the users, the computers attempting to access resources. Kerberos is an example of a protocol used for authentication that is also used by Microsoft Active Directory Domain Services. I call out those examples simply because they are so prevalent in the enterprise today. So federation. So federation is a collection of domains that have established trust. Now the level of trust may vary, but it typically includes authentication and almost always includes authorization. And it often includes a number of organizations that have established trust for shared access to a set of resources. For example, you can federate your on-premises environment with Azure Active Directory and use this federation for authentication and authorization. The sign-in method ensures that all user authentication occurs on-premises in a federation configuration. This allows administrators to implement more rigorous levels of access control. For example, to implement certificate authentication or key fob or card token. So just to conceptually visualize an example, let's say we have a website or an app or a service that authenticates with identity provider A, and we have a user that authenticates with identity provider B, and identity provider A is configured to trust identity provider B to provide shared access if the user authenticates successfully with identity provider B. So this may be a cloud or an on-premises provider. Do bear in mind that trust is not always bi-directional. So for example, the user could be authenticating with their Twitter account and we could configure Azure Active Directory to trust Twitter. And so federation would work in that scenario. So biometrics. This is authentication using an individual's physical characteristics which are unique to each individual. So there's a fingerprint scanner, which are now very common, and they're used not only in multi-factor authentication, but various travel, financial, and legal situations. So you'll see these at some airports and even at some banks. A retina scanner, which works with your eye, of course, and with appropriate lighting, the retina of the eye can be accurately identified as the blood vessels of the retina absorb light more readily than the surrounding tissue. Then there's the iris scanner that confirms the identity of the user by scanning the iris of their eye. Both retina and iris scanners are physical devices. Then there's voice recognition, where the voice patterns of a person can be stored in a database and used for authentication. Facial recognition, which looks at the shape of the face and the characteristics like mouth, jaw, cheekbone, and nose. Now, light and angle direction can be a factor here, especially in software. Microsoft's facial recognition solution called Windows Hello was released in Windows 10, and it uses a special USB infrared camera, so it's a little better than some other facial recognition programs that can have problems with light. You can look at veins, so using blood vessels in the palm can be used as a biometric factor of authentication. And then there's gait analysis, so that's G-A-I-T. Gait is the way an individual walks, and identification or authentication using gait is possible sometimes even with lower video resolution. So crossover error rate in the context of biometrics. So false acceptance occurs when an invalid subject is authenticated, someone who shouldn't have been. This is sometimes called a false positive authentication. Then a false rejection occurs when a valid subject is rejected. This is sometimes called a false negative authentication. So false acceptance is also known as a type 2 error. False rejection is a type 1 error. So false rejection is undesirable, but false acceptance is generally considered worse. For the exam, remember FAR as the acronym for false acceptance rate and FRR as the acronym for false rejection rate. And then there's the crossover error rate. This is in biometrics, identifying users based on their characteristics and then identifying the accuracy of the method. The crossover error rate is where false rejection and false acceptance rates are equal. So to move the crossover error rate lower or higher, you can increase or decrease the sensitivity of the biometric device until you get to that happy medium. And now moving on to multi-factor authentication, or MFA. So MFA works by requiring 2 or more of the following authentication methods. So at a high level, multi-factor authentication is something you know, like a PIN or a password, as examples. Something you have, like a trusted device, your mobile phone, for example. And something you are, a biometric factor, such as a fingerprint or thumbprint, which is very commonly captured on your mobile device. And we can leverage the Authenticator app for those tokens we talked about, the one-time passwords, the voice call, the SMS or text message. That Oath hardware token is also an option. But all of these factors together can obviously decrease the risk of an attacker authenticating successfully with stolen credentials. So it includes 2 or more methods, just to summarize here. 2 or more methods. It's more secure than a single authentication factor. Passwords are generally the weakest form of authentication. Password policies help increase their security by enforcing complexity and history requirements. Smart cards, including microprocessors and cryptographic certificates, give us another strong authentication factor. Tokens create one-time passwords, and biometric methods identify users based on individual characteristics like their fingerprints or facial recognition, retina or iris, and more. So breaking down the high-level MFA attributes that are called out in the exam objective. So somewhere you are, your expected location, like the company office, your home, or your city. Something you can do, such as writing your signature. So the speed of your signature and the appearance can be leveraged in attributes if desired. Something you exhibit, the personalized manner in which you perform an action, such as your gait, the way you walk. Someone you know, responding to a challenge with knowledge of a characteristic of a specific individual you know. A common challenge question is your mother's maiden name, the name of your first pet. I won't call those great factors for authentication, but those are attributes that can be tied back to specific knowledge that you have. So moving on, the AAA protocols. There are several protocols out there that provide centralized authentication, authorization, and accounting services. We see this commonly with a network access server. It's a client to a Radius server, and the Radius server provides those authentication, authorization, and accounting services. We see that often in conjunction with a VPN. So Radius uses UDP and encrypts the password only. So TACACS, we hear commonly in the Cisco world, it uses TCP and encrypts the entire session. And then Diameter is based on Radius and improves many of the weaknesses of Radius, but Diameter is not compatible with Radius. So network access or remote access systems tend to use these AAA protocols. So VPN is the first thing that comes to mind. So considerations and differences between authentication in the cloud or on-premises. Just a few things to think about here. The perimeter of on-premises location is easy to establish and control. And proximity cards like a badge system and security guards at a reception desk can also control access to the company, physical access controls. But it also, in that case, doesn't always assume that internet access is available. Now in the cloud, internet access is generally speaking assumed in order to authenticate and connect to cloud resources. And with the adoption of cloud computing, the security perimeter is no longer confined to the on-premises environment. And in fact, the zero trust model is recommended and has risen to prominence in the age of cloud computing, where nothing is trusted by default. And we frequently hear the phrase identity is the new perimeter when it comes to zero trust. So we see the boundary shrinking from the physical network perimeter down to identities, users, and devices. So let's talk about enforcing conditions of access. We see this pretty frequently in modern authentication platforms and providers, where signals can be processed in conditions of access. So a request, we can look at the user's location, the device they're coming in on. Is that device trusted? Is it managed? What application are they using? Is it a managed application? And in some cases, platforms will allow us to look at real-time risk. Is this user exhibiting some manner of risk in this request? Are they in this request exhibiting some anomalous elements that elevate their risk? And then we can make a decision here, verifying every attempt, potentially requiring multi-factor authentication, for example, if risk is elevated, or potentially even blocking access if risk is high enough, or if everything checks out in those signals, making the decision to go ahead and allow access and enforcing that access decision, whatever it is, for or against. But if the signals map to our requirements and there's no undue amount of risk or danger in the detected in the decision, we can then give the user access to apps and data. But it's really signals feeding into a decision which is then enforced for or against access. And moving on to section 2.5, given a scenario, implement cybersecurity resilience. So we're going to talk about redundancy, replication, and really considerations on premises versus cloud. But implement in the context of the exam really means choose the right option for a scenario. So disk redundancy. So if we go back to hardware in a traditional on-premises data center, RAID, redundant array of inexpensive disks, is a technology that's been around a long time and used to increase performance and or reliability of data storage with 2 or more drives working in parallel. Now there are RAIDs that we see commonly, RAID levels from 0, which is striping, which doesn't provide resilience, it only improves performance, to mirroring in RAID 1, all the way up to RAID 10, combining mirroring and striping, which was really the top of the mountain in the on-premises data centers I've worked in. But for storage, multipathing, also known as SAN multipathing or IO multipathing, is the establishment of multiple physical routes between a server and the storage device that supports it. Now, replication to another site for availability through site failures is common. In the cloud, this will come down to choosing a disk or storage tier or SKU. So with a virtual machine in the cloud, we can choose the level of performance and resilience for our VM disks, for example. You can even set up some advanced storage configurations that involve replication between physical sites, so between regions. Just note you're not expected to know the details of RAID levels for the exam. Know that fundamentally RAID allows us to build resilience into storage at a hardware level, and at some level in some form, your cloud service providers are going to be using some form of that capability for their underlying cloud infrastructure, the piece that you're handing over to the cloud service provider in that shared responsibility model. So network redundancy. So methods for building redundancy into network connectivity for systems and services. You have network teams, network interface cards, or NIC teams. These are dual network cards paired together to give maximum throughput, and you can configure those so should one adapter fail, the other can ensure the server or client maintains network connectivity. Load balancers can balance multiple types of traffic across multiple servers, and this includes logic to determine server availability. Generally speaking, many of your load balancers will give you multiple options for how you can select to have server availability determined. Load balancers are often used for web traffic, but generally support other protocols. A couple of side notes. So Windows and Linux both support NIC teaming, by the by. But these can help maintain service availability in cyber attack scenarios. So if you have a system that is compromised in some way, if it's a disruptive attack or other breach, these are just a couple of many technologies, resiliencies we can build in that may help us through that attack and maintaining service availability. So let's talk power redundancy for a moment. So the UPS, the uninterruptible power supply, this is essentially a battery. That is a standby device so that when primary power fails, it provides power. It's designed to keep connected systems running for a limited period of time, enabling graceful shutdown. And UPSs are also used to clean up the power coming from the grid, eliminating spikes, surges, and voltage fluctuation. So protecting systems and data from damage due to unexpected power outage. And the typical UPS will have network connectivity, so it is remotely manageable and can be monitored often by SNMP. So a power generator. So a generator, by comparison, is a standby power source that is powered by diesel, gasoline, propane, natural gas, or potentially other fuels. And when the power from the grid fails, it can be started to provide electricity for an extended period of time. Generators are used by hospitals, data centers, and other facilities hosting critical services. The key here is it provides sustained alternate power to support continued operation in the event of an unexpected power failure, whereas the UPS is really designed just to accommodate a short run and graceful shutdown to avoid damage to hardware and data. Most servers will have a dual power supply so that if one power supply fails, then the other power supply keeps the server running. And then we have managed power distribution units, or PDUs. A PDU is a device that provides multiple power outlets for power cable plugs, and a managed PDU includes network connectivity for remote connection and management of those power outlets. So imagine a smart network-connected power strip. You'll see PDUs often mounted in the back of server racks in a data center, and that network connectivity and remote management capability allows us to connect and control the power to specific outlets on the PDU. And PDUs generally distribute clean power to your resources, and if you're plugging in critical network resources like your servers, your routers, your switches, and other data center components, having clean power is going to be very important. So let's talk about replication. So this is where data is copied from one location to another. So in storage scenarios on premises, a storage area network, or a SAN, is a hardware device that contains a large number of fast disks, like solid-state drives, usually isolated from the LAN on its own network. You'll typically have dedicated network connectivity for the SAN. And the servers that connect to that storage device, to that SAN, connect to the SAN with host bus adapters, or HBAs. Using two HBAs with each server node provides multiple paths to the storage area network. And SAN fabric refers to the collection of servers, storage, switches, and other devices. Redundant SAN fabrics would enable a more robust redundancy. And in fact, in this fabric, switches are mentioned because your SAN will have dedicated SAN switches that are function specific for this configuration. And SAN nodes with one HBA connected to SAN Fabric 1 and another connected to SAN Fabric 2 would provide redundancy, and we can replicate data between those SAN fabrics to provide service level resilience. And we can handle that replication between SAN fabrics in a single data center, or we could take that to a remote data center to facilitate continued service operation through site failure. And then there's virtual machine replication. This is where a copy of a VM is copied across to another physical host, another server hosting the hypervisor. Now with live migration, VM files can be copied across onto a second physical host with no downtime. This is a common feature in your enterprise Type 1 hypervisors, your bare metal hypervisors. Now with SAN migration, the files for a virtual machine are not copied from one server to another, and thus downtime is minimized because each node in the hypervisor cluster can see the storage LUN and has a cluster disk resource for the LUN. So VM migration in this scenario simply means transferring control of the backend storage from one hypervisor host to another. A SAN, a storage area network, which we just talked about, is a common storage backend for a hypervisor cluster. And while the terminology differs slightly by vendor, this capability exists for Hyper-V and VMware and other popular Type 1 hypervisors. Really, Hyper-V and VMware tend to be the two primary games in town when it comes to Type 1 hypervisors. And moving on to cloud versus on-premises when it comes to data resilience, we can think about the advantages in a hybrid cloud scenario. We could consider hosting a backup of our on-premises environment in the cloud. We can replicate data and virtual machines from on-premises to the cloud. So if we have a disaster, we could simply flip the switch and move to the cloud. And the way we see that play out often in a disaster scenario, say a data center affected by a tornado, if we have backup office space or if our workers can work from home, we can simply change some DNS entries, flip some switches to bring that public cloud infrastructure on as our active environment and have folks working from home or potentially working from backup office space that's been leased in advance in preparation for a disaster, maybe across town away from the office that may be impacted. And the replication in this scenario, at least with virtual machines, tends to be agent-based replication. It tends to be simplified in some fashion. It may be replication that's happening directly from the host, the hypervisor itself, or maybe through some central agent that's channeling that replication from multiple hypervisor hosts. But usually it's a simplified operation in some form. Now, if we think about cloud native, public cloud, storage replication in the cloud between cloud data centers, between regions, is often a simple service level selection. If I pick the right level of cloud storage, it's going to be handled for me without really any configuration or heavy knowledge on my part. And VM replication in some respects will also be greatly simplified. Now, I think that's less true if we think about replicating from, say, AWS to Azure or vice versa. But within a single cloud service provider, definitely it's going to be simplified, setting up that resiliency to plan for an entire site or region outage with our cloud provider. This reduces infrastructure complexity, but do know that when you pick those advanced features in the cloud, they're going to come at an additional cost. You're paying for what you use, and that advanced functionality will not be free. So moving on in section 2.5, just continuing here, given a scenario, implement cyber resilience. Let's talk about backup types, non-persistence. The A in the CIA triad is availability, by the way. So resilience and availability very much speak to security. The C and the I being confidentiality and integrity. But CIA triad a discussion for another day. Let's talk about backup types. So called out in the objectives, we have tape backup. This is backup to magnetic tape. It would be the slowest form of restore by a significant margin in most cases. It can be stored off-site with a vaulting service and a fireproof vault, so that's certainly a positive. With disk backup, we can back up to a USB drive, a removable hard disk, or a disk on another server. We can make a copy using Xcopy or Robocopy or other copy utility to copy to another server on the network, for example. We could even copy into a network share, for example. This is useful in one-off or ad hoc scenarios. Sometimes I've even seen it used in provisioning. It's not going to be a standard for scheduled backups generally. Network attached storage. This is going to be useful when data is accessed using a UNC path rather than a LUN, as with a SAN. And network attached storage is going to tend to be a good solution for a large volume of data if we're working with multiple terabytes, for example. So the storage area network, good for fast backups of large data sets, common with SQL databases or for organizations hosting their email on premises. Also enables tiered storage access for prioritizing by workload. And tiered storage access is a moving target. You'll find many options for tiering storage out there to have cool, warm, and hot tiers based on access, so you can put your heavy processing, your highest performing disks behind the hot tier. So continuing down the backup types, we have cloud backup. So backup to cloud storage for multiple scenarios. For user file solutions like Dropbox and OneDrive, enable automated sync and versioning at an individual user level. Cloud backup solutions support server and file share backup. So for an individual user, just synchronizing their OneDrive is a solution. But to, say, facilitate faster recovery from a ransomware attack, we might buy a third-party solution that allows us to back up all of our Office 365 files. Imaging, so a clone of an operating system to enable quick restore of the image to bare metal is handy. If you have remote office workers that are difficult to get to, giving them an image of their own system might even be a viable option. Offline versus online. So offline media needs to be labeled and securely stored. Online backups are going to be faster to restore. So a form of offline backup is tape. If we have to go to the fireproof vault to the third-party service to retrieve that tape or have them bring it to us, that's going to slow the pace of restore, of course. And always distance and bandwidth should be considered in planning for your recovery. Planning your recovery time and recovery point. Travel time for retrieving tapes or copy time in retrieving data from the cloud are both going to be factors. So non-persistence. This refers to systems that are not permanent and can be returned to a previous state. So reverting to known state. In a Windows environment, you can save the system state and the system settings to removable media. And if the computer is corrupt, you can then repair the computer and insert the media and revert to the system state. The last known good configuration is where the system has recorded the configuration state as you log in, and this can be reverted to at a later stage. And in fact, in Windows, new last known good is created at each login. So you have a new last known good configuration every time you log in successfully. Live boot media. This is a copy of the operating system saved to a USB flash drive or a DVD. It enables booting from the removable media. So let's talk through some concepts related to cyber resilience. So high availability is called out. Now scalability refers to the ability of a system to handle growth of users and work. This is about scaling up to handle greater load. We then have fault tolerance, which speaks to the ability of a system to handle faults in a service like power, network, and hardware failures. This typically refers to component level failures. High availability is the ability to keep services up and running for long periods of time. This generally refers to resiliency through service level failures. Disaster recovery. This is about the ability to recover from an event which has taken down a service or a site. But when we talk about disaster recovery, we're typically talking about recovery in the event of a service or site failure. So restoration order. This is establishing the order in which components, systems, and services should be restored based on defined criteria. So prioritizing sequence can be based on business impact analysis, so the most critical systems will be restored first typically. And we'll base decisions on metrics like the recovery time objective, which is the maximum amount of time a process or service is allowed to be down and the consequences still to be considered acceptable. So this is service focused, and in the case of some services that are sold to third parties, there'll be a recovery time objective written into the contract, beyond which the service provider moves into a penalty phase. And then we have the recovery point objective, or RPO. This is a point of last known good data prior to an outage that is used to recover systems. This really also tells us the time that can pass before the data loss exceeds maximum tolerance, but this is data focused. And diversity. So the impact of diversity on availability, resiliency, and security. So there is vendor diversity, which involves getting a service from multiple providers at the same time. So this would be really common on premises in contracting internet connectivity from multiple providers. Maybe you get one from Xfinity and then another from AT&T. So you have two lines, different providers, and that diversity provides greater resilience. Technology diversity, so different technologies in service delivery, different OSs, apps, appliances, etc. Crypto diversity. This is when a company uses multiple algorithms to protect their data, or multiple layers of cryptography. And then controls diversity, which implements a compensating or a backup control that could replace a primary control should it fail. So for example, maybe an organization has a separation of duties policy for someone in IT security, and maybe that second person that's there to verify a process is out of the office or sick that day, and so it's not possible to implement that control as it was written. So maybe the backup policy is that one person that's left, in order to execute that process, has to take the request to their manager for review in order to satisfy that initial control. So it's a backup that could replace the primary should it fail. There can be a lot of examples in the world of information security. But diversity can improve security and resiliency if it is well managed. If it's poorly managed, some of these can lead to management complexity and poor integration. So moving into section 2.6, we'll be explaining the security implications of embedded and specialized systems. So here we'll touch on embedded systems, Internet of Things, and supervisory control and data acquisition, or SCADA. So an embedded system is a computer system that has a dedicated function within a larger mechanical or electronic system. And in fact, the technology component of an IoT device is often referred to as an embedded system. It's a full computer system embedded inside another larger system. A few examples of those larger systems that host an embedded system include printers, GPS, drones, and semi-autonomous vehicles. But an embedded system is both hardware and software combined into a single device. Some of these devices will have an update capability, some will have no update mechanism, which makes them more vulnerable to attack over time. The longer a system is around without updates, the more likely someone will eventually exploit a vulnerability. So we have the Raspberry Pi, which is a credit card-sized computer that allows you to run programming languages such as Python or Scratch, and it can be plugged into a monitor or a computer if you like, and typically run with relatively low power draw. And then there's the field programmable gate array, which is an array of programmable logic blocks designed to be configured by customer or designer after manufacturing. It accepts custom code and stores it in multiple hardware blocks. But it's very flexible in that it allows field modification to your use case. That's why it's field programmable. Then there's the Arduino. This is an open source programmable microprocessor or microcontroller. The boards are programmable through a USB. You can read inputs such as a light on a sensor or an activity such as turning on an LED, publishing something online, or activating a motor. Now, I've seen them used in agriculture scenarios to drive water monitoring, as an example. But you can run these from a 9-volt battery. They can be used to control electronic components. And the Arduino has shields, and these allow you to add wireless or Bluetooth, so it could be used even to build a robot. So next up, we have the Supervisory Control and Data Acquisition, or Industrial Control Systems, SCADA and ICS. So you'll find SCADA systems in places where there's a large amount of industrial equipment. In an industrial manufacturing or public utility setting, equipment is often network connected and monitored. And it can all be centrally configured and controlled and monitored from a computer using a SCADA network. But that central configuration, control, and monitoring is a key aspect, a key characteristic of SCADA. They usually don't have direct internet access for greater security. That's not surprising, I think, given they're commonly used in industrial, manufacturing, or public utility settings where there's certainly a lot at stake. Public safety is involved. They should be segmented off from the rest of the network generally and protected by security controls to restrict access. Internet of Things. So this is a class of devices connected to the internet in order to provide automation, remote control, or AI processing in a home or a business setting. More scenarios involving IoT devices are likely to appear in the 2021 exam update for Security Plus. Now, smart devices are mobile devices that offer customization options, typically through installing apps, and may use on-device or in-the-cloud AI processing. A smart device has 3 main features: context awareness, autonomous computing, and connectivity. That being said, many devices can be called smart if you add a sensor, a tiny bit of computing capabilities, and network connectivity. In that context, I could make a chair smart. Digging into Internet of Things, weak defaults are mentioned on the exam objectives, and every device that you put on your network to manage has a default username and a default password. Often the defaults are open and available for anyone to use. The Wi-Fi might be open. IoT devices may have a well-known username and password. And one of the dangers here is botnets and offensive security tools will find and exploit devices with weak default settings still in place. The good news is, to close that door, you simply need to change the default and you shut down that attack vector. In business scenarios, I find those default settings linger due to process issues. Now, if you have sound configuration management and change management processes in place and you enforce those standards, you're not going to have problems with default settings. Wearables, that category would include your fitness tracker or your smartwatch. Facility automation, so in a large facility, IoT devices are able to manage everything from heating and AC to lights to motion, fire, and water detection. And often they're fairly simple to program, enabling facility managers without specialized training to be able to configure automation and monitoring of device function. Sensors come up as well. So vehicles are an example of systems with specialized sensors embedded assisting with vehicle function. But let's unpack that specialized category. So medical systems are a broad category that cover everything from small implantable devices to tools for measuring vital signs to MRI machines. And an issue is how to patch the discovered vulnerabilities in these systems, because even if they're patchable, there's considerable testing required to ensure human safety. The same is true for automobiles. Our automobiles have very specialized and multiple embedded systems, as I mentioned, and today almost every aspect of the car has sensors that are monitoring function or surrounding, and some of these communicate with each other to make the driving experience safer. And so while they need that network connectivity, security updates and network security are going to be major concerns in securing specialized systems. I think we've all probably seen a YouTube video or heard a story about someone hacking a semi-autonomous vehicle or just a modern vehicle out there that has these sorts of systems. And with medical systems, we have to think about patient health, and with medical systems, human life is at stake in another level. There's certainly a concern in automobiles. With medical systems, we're dealing with patients in hospitals, so it's a little more widespread and a little more sensitive yet. Aircraft. So we have a similar set of embedded systems and many different networks and sensors all communicating amongst each other. So the testing you'll see in the airline industry will include trying to get to these specialized embedded systems through, say, passenger Wi-Fi. So you'll see penetration tests conducted to make sure that the passenger Wi-Fi is appropriately segregated from the core systems that run the aircraft. Again, dealing with human safety. Smart meters. So in homes and businesses, we're starting to put more and more sensors on our utilities and increasingly embedded systems that are watching water, electrical, and other types of utility use. So protecting against denial of service attacks is going to be of paramount concern in all of these systems. When we have embedded systems that are communicating to ensure vehicle operation, such as in aircraft or automobiles, making sure that they're able to communicate, that they have processing power, that they have adequate network bandwidth is going to be very important. And in addition to secure network access, ensuring device access is secured will be important. And oftentimes you're going to need to work with the manufacturer because there might not be a lot that you can configure on these devices beyond what comes from the facility, from the manufacturing facility, that is. Voice over IP or VoIP. These are embedded systems for voice communications and more. So IP phones can be entry points into your business network and are susceptible to data network attacks. So you can use security features on VoIP systems to restrict system access, to limit call types and call hours, preventing long-distance calls that may carry a fee. All of those security features can help us in shutting down attack vectors, so if an attacker were to gain access to a system, we can limit what they're able to do with the system they've compromised. And ensure users delete sensitive voicemails when they're no longer needed. Again, that comes down to the information lifecycle. The last stage of the information lifecycle is destruction, and keeping data around longer than it's needed increases our business risk. I think the bright spot with VoIP phones is that they're essentially standalone computers, so we can use many of the same security controls you would employ to protect a typical computer network. Firewalls, intrusion prevention systems, applying updates, and restricting network access. So continuing down the road of embedded and specialized system, we're going to touch on a handful of additional embedded systems. We're going to talk through communication considerations and the constraints of these systems. So continuing down the list of devices, let's talk about heating, ventilation, and air conditioning, or HVAC systems, which come up often in business and data center scenarios. These tend to be very complex systems, especially in larger environments, and they're often integrated with the fire system as well. And in large HVAC implementations, they have a computer that monitors and maintains all of the heating, ventilation, and air conditioning for the facility. So as these systems play a role in human safety, security in HVAC and HVAC monitoring is going to be very important. Unauthorized access by an attacker may allow full control of the system, and that has potentially disastrous results. If they can turn off alarms, if they can change the heating in a dangerous direction, we can definitely see a negative impact to human safety. Now, smart buildings allow turning these HVAC systems on or off based on occupancy and use. This reduces cost, but internet or even network access adds risk, and we have to bear that in mind. Now, the security implications of embedded systems are of special concern with drones as well. These may be devices that are manually controlled, but some have autonomous functions, not requiring human interventions. And in the United States, you have to have a federal license to be able to fly one of these drones of a certain size. It's very common to find security features and fail-safe functionality built into drones, and that way If anything occurs while this device is in the air, you can land it safely without harming anyone in the vicinity. And you want to consider those features when you're selecting these devices. So in a multi-function device, you can have a scanner, a printer, and a fax machine all within a single embedded device. These devices have become increasingly complex with very sophisticated firmware. The scans and faxes are stored somewhere on the device, usually with internal memory in this multi-function device. And they generally feature bidirectional communication with user endpoints for document sending and retrieval, which opens the door to attackers. So logs on this device can also provide an attacker with a list of users and endpoints the device is communicated with. All considerations to bear in mind. Now, real-time operating system, or RTOS. So smart devices like wearables and embedded systems, like in cars and industrial equipment, often use a real-time operating system. It's an operating system that's designed to work on a very deterministic schedule. That means the hardware and software of this device is able to operate with very specific scheduling. So security of these devices is important, but it's often difficult to know exactly what's running inside those embedded systems. But in a real-time operating system, they process data immediately, and if the task of the process doesn't complete within a certain time, the process fails. So surveillance systems, the cameras and the monitoring systems used for video surveillance, are also embedded systems. And some of these are high-end, feature-rich, and expensive, often with advanced networking to protect their content, to encrypt the video that's streaming from them. Others are cheap, ubiquitous security cameras you buy off the shelf at the local electronics store, used for surveillance at home or in a variety of less critical public scenarios. The nicer cameras may have motion-sensitive or motion-activated functionality or even object tracking capabilities. It's important to ensure that the proper access security is implemented so that only authorized users can view camera data. Going to be very important. And due to location, often on the roof or building exterior or near a ceiling, remotely upgradable firmware and patching would be very desirable. So it's a feature you want to check into. Certainly in a business setting, I'm going to make sure I'm checking to see that these devices are properly upgradable in a pragmatic and sustainable way. So system on chip is used in a variety of embedded systems and smart devices. It's a complete computer system miniaturized on a single integrated circuit, providing full computing platform on a chip. It includes networking and graphics, though the memory may be located elsewhere. System on chip are very common in the mobile computing market, and there are billions of these devices worldwide. It has multiple components on the single platform, and often a single chip may handle multiple functions on that single board. They're common in embedded systems primarily because they are widely available, multifunctional, and customizable. So let's touch on communication considerations. We'll start with 5G, fifth generation cellular. So unlike 4G, we have faster speeds, lower latency, and 5G doesn't identify each user through their SIM card. They can assign identities to each device. Some air interface threats, such as session hijacking, are dealt with in 5G. The standalone version of 5G will be more secure than the non-standalone version, and over time all the providers will get that non-standalone version rolled out. You'll see that non-standalone version in the earlier days, and NSA anchors the control signaling of 5G networks to the 4G core, which brings with it some legacy security concerns. So the diameter protocol, which provides authentication, authorization, and accounting, will be a target. Because 5G has to work alongside the older tech, old vulnerabilities may be targeted. And because the scale of IoT endpoint counts on 5G is exponentially greater, distributed denial of service is going to be a concern. So takeover and driving DDoS with botnets with large fleets of compromised devices is going to be a threat. Some carriers originally launched an NSA version of 5G, which continues to rely on availability of that 4G core. From a security perspective, we'll be glad to see that go away. So narrowband. So this refers to radio communications that carry signals in a narrow band of frequencies. It's used in a variety of scenarios requiring short-range wireless communications. Good examples would include RFID or keyless vehicle entry products. Now, DDoS attacks that disrupt communications impacting device function or sending telemetry are going to be a major concern where narrowband is involved. Baseband radio. So this is used for audio signals over a radio frequency. It's transmitted over a single channel, and it uses that single frequency for communication, and it is digital. An example would be truck drivers communicating with one another over a specific channel. That's conceptually what we're talking about there. Then we have the SIM, Subscriber Identity Module Card. So the SIM card, the small computer chip that contains information about your mobile subscription. It allows a user to connect to a telecommunication provider to make calls, send text messages, or use the internet. So SMS messages can be used as a second factor in authentication. So that involves the SIM card today. It's one of the authentication factors most prone to attack and is therefore widely recommended as one to avoid in your multi-factor scenarios. The SIM card hijacking has been proven out in a real-world scenario. Li-Fi, light fidelity, uses the modulation of light intensity to transmit data. It uses LED. It can safely function in areas otherwise susceptible to electromagnetic interference. I think that is a capability worth remembering. It can theoretically transmit data at speeds of up to 100 gigabits a second. Do bear in mind, Li-Fi only requires working LED lights, but visible light in that it cannot penetrate opaque walls. It's light. So Zigbee, which is a personal area network. It's a short-ranged wireless personal area network developed to support automation, machine-to-machine communication, remote control, and monitoring of IoT devices. It supports centralized and distributed security models and a mesh topology. It assumes that symmetric keys used are transmitted securely, that they're encrypted in transit. So during the pre-configuration of a new Zigbee-capable device in which a single key might be sent unprotected, you've got a brief window of vulnerability there. A common use of Zigbee is in IoT smart home hubs. In fact, there are certain Alexa models that have a Zigbee hub built in. So let's talk constraints in embedded systems. There are quite a few constraints in embedded devices due to their size, their location, their cost, their architecture. These include, for example, power and compute. The device is limited in size and often sits in remote or unusual locations, so this results in limited compute capacity and the need for low power consumption. Network connectivity. Embedded systems are not scalable, and some can only communicate through Wi-Fi or Bluetooth and are often short-ranged. It's difficult to transfer data from one system to another often. Authentication. Some embedded systems are incapable of joining a network and may only support local logon. You know what to do there. Change the defaults. So cryptography. PKI needs at least a 32-bit processor, and embedded devices are generally limited to 8 or 16. So as a result, authentication may be very slow depending on the type of authentication. So hardware upgrade and patching. Most embedded devices can't have their hardware upgraded and may require physical access to patch. And some vendors may not produce patches. So all important considerations. Many have that very short range, so they're not very flexible or scalable in terms of management and use. In terms of cost, they're mainly customized and function specific to keep costs down, making upgrade to new hardware versions impractical, sometimes from a process perspective, but often from a budget perspective. Implied trust. It may not be feasible to troubleshoot these devices. So when you purchase an embedded system, there's an implied trust that the system functions as documented. You may want to ask the manufacturer if they've pen tested the device, if they've made sure that it's hardened to a sufficient degree. That does it for lesson 2.6. We're going to move into section 2.7, explain the importance of physical security controls. So explain the importance means you need to know not only what, but why these components are important and where they factor. But we'll make sure you have the key points locked in for the exam. So we'll start with the functional order of security controls. And this is really just some background to give you a leg up. So security controls really work in this order. So we start with deterrence, and if we can't deter or discourage someone from an action, then we have denial. So we try to stop the action. And if denial fails, then we want to detect the action. And with detection comes then the need to delay their capability to complete whatever that attack is they're attempting to carry out. So this is really the logical flow in terms of the security controls we're going to layer in to our physical security. So defense in depth is the concept of protecting a company's data with a series of protective layers. And if one layer fails, another layer will already be in place to thwart an attack. And physical security plays a role in data security and service resilience and other areas. And understanding the types of security controls can be a major advantage in your cybersecurity career, and it can make it easier for you to understand physical security as a whole for the Security Plus exam and others. So physical security controls can be divided into three groups at the highest level. You have operational controls, which may also be called managerial or administrative controls. This will include things like policies and procedures, like site management, personnel controls, awareness training, and emergency response and procedures. And we have logical controls, also known as technical controls, and these are implemented through technology like access controls, intrusion detection, alarms, closed-circuit TV, monitoring, HVAC, power supplies, fire detection and suppression. And then we have the third group of controls, and these are physical controls. This means to protect objects, and this includes fencing, lighting, locks, construction materials, man traps, dogs, and guards, to name a few. So you want to know the logical controls for physical security for sure. So these, like I say, will include access controls, intrusion detection, alarms, CCTV, HVAC, and power supplies. I want to lay these out so you have some nice study aids. Administrative controls. So facility construction, selection, your site management, personnel controls, awareness training, emergency response, emergency procedures, so anything policy related in that case. And then we have the physical controls, so fencing, lighting, locks, construction, man traps, dogs, and guards. So there you have those laid out for study. Now, do remember there is no security without physical security. Without control over the physical environment, no amount of administrative or technical logical access controls can provide adequate security. If a malicious person can gain physical access to your facility or your equipment, they can do just about anything they want, from destruction to disclosure and alteration. So bollards and barricades show up on the exam objective. So what is a bollard? Well, it's a short post, or really a row of short posts, typically used to divert vehicle traffic from an area or road. They can be placed in front of a building to stop a car from driving at a desired point, to prevent a car from driving into a building, as you'd see in the picture there. It may be used also to establish different zones of physical security. I've even seen them made so they can come out of the ground on demand, so they can be lowered and raised as necessary to establish those zones. But for the exam, I would make sure that I'm familiar with the different physical controls related to entry and entrance security. We're going to talk about a few of those today. So the access control vestibule. It's a turnstile device that allows only one person in at a time. A man trap is a common example. An airlock is a similar concept that also restricts airflow. So for purposes of the exam objective called out access control vestibule, man trap is the same as access control vestibule, two terms for the same thing. In fact, I believe you'll find that to be true even on Wikipedia. So badges, signage, and alarms. So signage, before anyone reaches your main entrance, there should be highly visible signs warning them that they are entering a secure area with armed guards and dogs. This is used as a deterrent to prevent possible intruders, to discourage intruders. Remember back to the order of security controls. And then badges, the form of identification that's retained or captured and photocopied. And then the user is allocated a visitor's badge that is a different color to that of employees. And typically in the badge scenario, they should return the badge when they leave. The badges should be visible at all time. And anyone that isn't displaying a badge should be challenged. In fact, you want to train your employees in this behavior to make sure that they adapt that as part of their culture and they help you in maintaining physical security in that way. For staff, badges for members of staff, for employees, they might be RFID-enabled cards so they can access the building via a card reader that would require physical proximity, a badge system, or maybe even an insertion of that badge. Burglar alarms, enabled when the premises are not occupied. So when someone attempts a break-in, it will trigger an alarm and notify the monitoring company or the local police. And then fire alarms and smoke detectors. So in a company building, there should be fire alarms or smoke detectors in every room. So when a fire breaks out and the alarms go off, people inside the premises are able to escape. Your number one responsibility in security: human safety. Cameras. So these are detective and deterrent controls for physical security. So some cameras are motion sensing. They can be set up in areas around the perimeter and on doorways to detect motion. Others have object detection and tracking capability. They can be set up to detect objects both day and night and to alert the security team by raising an alarm. Now, object detection and higher quality cameras can recognize the type of object sometimes, like telling a person from a vehicle. And it may be able to lock onto an object, like a person's face, and track it as it moves from place to place. CCTV, closed circuit television. You should consider monitoring entry points with CCTV. Through CCTV, you can compare the audit trails and the access logs with a visually recorded history of events. So it's going to allow us to compare the audit trails and access logs with a visually recorded history of events. So those logs are useful tools for managing physical access control. And you may need to create logs manually with your security guard's help, or sometimes logs will be generated automatically, like if you have an RFID badge system with proximity readers, the logging may be automatic. And you may find that functionality works to your advantage even with your visitor badges in a proximity readers. When the visitors walk by certain areas, that badge automatically gets picked up. That can be a valuable logging mechanism to track their physical access if you're not using cameras to do so. But through CCTV, you can compare the audit trails and the access logs at your entry with a visually recorded history of actual events to piece together the recreation of events, should that be necessary in terms of reconstructing a timeline of events in intrusion, breach, or attack. Industrial camouflage, so designing a facility or another resource to obscure it from identification via aerial photography and other means of observation. For company facilities housing important resources in operation, this may include designing the building to prevent recognition of its purpose. This is another layer of physical security. And entrances may be disguised as well to prevent visual identification by potential attackers and intruders. You'd likely also avoid placing signs that explain the purpose of the facility or the resources it contains. You don't want to advertise what needs to be attacked, what is worthy of attack. And the need for secrecy will also influence physical security decisions, like your fencing, your lighting, and your camera selection. So let's talk about personnel in physical security. So we have guards who work at the entrance reception desk to check the identity of people entering the building to stop unauthorized access. And in high security scenarios, an armed guard and a dog may be appropriate. Generally speaking, 2 guards at reception are an excellent idea, and procedures for staff and visitors should be clearly defined. Robot sentries can be used to patrol the facility perimeter and raise warnings to deter any intruders or alert security staff. Any mention of reception is that desk or station at the facility entrance where guards will check employees and visitors. Two-person integrity and control. This ensures that no single person would have access to any particular asset in the building that needs to be protected. It also reduces the risk of a malicious insider attack. Threats to physical access control. So no matter which physical control is used, a security guard or other monitoring system must be deployed to prevent abuses of physical access control, including propping open secured doors and bypassing locks or access controls, or masquerading, which is using someone else's security ID to gain entry to a facility. Piggybacking, which is following someone through a secured gate or doorway without being identified and authorized. Now, all of these are related to badged entry, and certainly we can look at advanced camera functionality to help with some of this, but a security guard is going to be a very reliable backup to spotting these sorts of abuses. The exam objectives call out 4 types of locks you should be familiar with, the first being biometric locks, so something you are, so something unique about your person or behaviors. Electronic locks, something you have, usually a PIN code. Cable locks, which are attached to laptops or tablets to secure them against theft. That picture you see there is an example of a cable lock for a laptop. And then physical locks, a device that prevents access to data, such as a key lock switch on a computer. So USB data blocker. This is a device that blocks the data pins on the USB device, which prevents attacks in unsecure scenarios. For example, this can prevent juice jacking, where data is stolen when you're charging a USB device in a public area like an airport. Let's touch on the basics of lighting and security that I believe will be useful for the exam. Attackers will typically avoid any place that's lit because they don't want to be seen. So proper lighting is one of the best security controls you can implement, particularly in environments that need to be monitored 24 hours a day. And you want to make sure you're providing enough light levels for the cameras and guards monitoring that area. And consider lighting angles, especially if there are shadows and you're doing some type of facial recognition. Now here's some extra credit. This may not come up on the exam. I think it will be useful knowledge for you going forward in your career just the same. These are some elements of effective lighting design. So the lighting should not illuminate the positions of the guards, dogs, patrol posts, or other similar security elements on the exterior of the building. That's going to tip off potential intruders. Lighting used for perimeter protection should illuminate critical areas with 2 feet of candle power from a height of 8 feet. And light poles should be placed the same distance apart as the diameter of the illuminated area. So 20 feet of coverage means poles 20 feet apart. So fencing basics. So fences protect resources for which access should be restricted. And they also advertise that you have something in this area that you don't want people to gain access to. Now, if it's okay for people to be able to see into a particular area, then you might want a fence that you can look through, which can help police, fire, and security professionals in some cases as well. An opaque fence that prevents seeing what is behind it will prevent anyone from seeing its contents if it's tall enough. Height and material will factor in how effective a fence will be in access prevention. So multiple physical security controls, fencing, lighting, and cameras together can collectively improve their effectiveness. Now let's talk about the efficacy of fences by height. So 3 to 4 feet of fence will deter the casual trespasser. A fence that is 6 to 7 feet tall is too difficult to climb easily, and it may block vision, providing some additional security. So most people are not going to be much taller than 6 feet on the average. An 8-foot fence topped with barbed wire will deter determined intruders. And there's also a control called a PEDIS, a Perimeter Intrusion Detection and Assessment System, which will detect someone attempting to climb a fence. Those are expensive and they may generate false positives, but if security is important enough for an area, it may be a control you are interested in. The fence is a deterrent control. The PDIS is a detective control. And technically an 8-foot fence is the height you need for those determined intruders. Fire suppression basics. This is going to be important for the exam, I believe. So fire is one of the worst case scenarios we have to plan for to protect human safety. So first, with proper monitoring and warning consisting of fire detection and alarm. Next, clearly marked fire exits ensure both employees and visitors can find safe egress from facilities in the event of a fire. And when a fire is detected, suppression will vary by the nature of the fire. Different materials, electronics, oil, chemicals, etc., require specific response. So let's talk about damage from fire and a little more on fire suppression. So the destructive elements of a fire include smoke and heat, but also the suppression medium, such as water or soda acid, can do damage. So smoke is damaging to most storage devices. Heat can damage any electronic or computer component. Suppression mediums can cause short circuits, initiate corrosion, or otherwise render equipment useless. And all of these issues must be addressed when designing a fire response system. Remember, the number one concern of security is always human safety. And this next bit around fire suppression, I'm going to call extra credit. I don't believe this is going to show up on the exam. I'm going to put it out here for your information. It's going to be good knowledge to carry forward in your career in the long term. So we're going to talk about the classes of fire suppression agents. So you have Class A. Class A fires are common combustibles such as wood and paper. This type of fire is the most common and it should be extinguished with water or soda acid. We have Class B fires. These are burning alcohol, oil, or other petroleum products such as gasoline. They're extinguished with gas or soda acid. You should never use water to extinguish a Class B fire. Class C are conductive. These are fires with electrical components, which are fed by electricity and may occur in equipment or wiring. Electrical fires need an extinguishing agent that is non-conductive, such as any type of gas. Class D, these are fires are burning metals, and they're extinguished with dry powder. And then finally, we have Class K, which are kitchen fires, such as burning oil or grease. Wet chemicals are used to extinguish Class K fires. The three categories of fire detection systems include smoke sensing, flame sensing, and heat sensing. So here's a quick table of fire extinguishers and suppression agents. So the short version here is for those Class A fires you can use water. It's water or soda acid. You don't use water on B through K though. But again, call these details extra credit. So continuing with section 2.7, we're still talking about physical security controls. We're going to touch on sensors, secure areas, secure data destruction, and a few other important physical security controls. So let's start with the role of sensors in physical security. So we have motion detection. So when someone is walking past a building and the motion sensors detect movement and turn on lights to discourage would-be intruders. That's a deterrent control. A building with a CCTV camera in a prominent position and a sign warning people they are being recorded may also act as a deterrent. Then there's noise detection. So noise monitoring devices can detect excessive noise to detect a variety of issues depending on where they're placed, including intruders maybe breaking a glass or other negative or destructive events. Proximity readers and cards. So proximity cards are commonly used to gain access to doors or door locks. So RFID proximity readers are a sensor of a sort. By moving the card close to the proximity reader, info on the card is checked, and then the system can either allow or disallow access through that lock based on the information related to that individual. So humidity sensors measure the amount of moisture in the air. And if there's too much moisture in the air, it can lead to condensation, which can damage sensitive equipment. It can lead to the formation of harmful mold. Now, temperature sensors detect that it's getting too hot, and it can trigger corrective action like injecting cold air into a space. Critical systems could fail if the temperature gets too hot. Carbon dioxide sensors measure the CO2 in the air, as workers could become ill with headaches or get drowsy if CO2 levels get too high. As with most security processes and equipment, sensors require ongoing maintenance and management and periodic testing. You need to make sure they're working, just like your smoke detectors. So no ideal levels, as well as the effects of temperature and humidity. I think these are easy facts to remember and useful. So humidity, 40 to 60% is ideal. Temperature for computers ideal is 60 to 75 Fahrenheit, so that's 15 to 23 Celsius. Damage really kicks in at 175 Fahrenheit and up. Managed storage devices, though, can be damaged at as low as 100 Fahrenheit. So too much humidity can cause corrosion. Too little humidity causes static electricity. Remember, 40 to 60% is ideal. Even in non-static carpet, low humidity can generate a 20,000 volt static discharge. So drones in physical security. Drones are used to monitor facility perimeters and conduct constant surveillance over large areas. It can also be sent out as a response mechanism before personnel can respond and conduct an initial site assessment. So you can send that drone out ahead as an element of advanced data collection to ensure the safety of your security personnel, because it enables the personnel to assess the risks before responding or entering a secure area where there may be danger. Visitor logs. So understand how to handle visitors in a secure facility, definitely on the exam objectives. If a facility employs restricted areas to control physical security, then a mechanism to handle visitors is required. Often, an escort is assigned to visitors, and their access and activities are monitored closely. Tracking actions of outsiders when they are granted access to prevent malicious activity against the most protected areas is expected. And visitor logs. Again, the guards maintain entrance to the base or company will ask visitors to complete the visitor logs and then provide some sort of authentication. Faraday cages. So Faraday cages are an enclosure used to block electromagnetic fields. It prevents wireless or cellular phones from working inside the enclosure. However, signals such as high-frequency RFID are likely to break through a Faraday cage, just FYI. A screened subnet. This is a boundary layer between the LAN and the WAN, the local area network and the wide area network, that holds information that companies may want people from the internet to access. Front-end web and email servers may reside in a screened subnet. Systems with sensitive data or hosting identity and access management would not. For example, Active Directory domain controllers don't belong in a screened subnet. Other names for a screened subnet are demilitarized zone, DMZ, or perimeter network. So those are all different terms for the same concept. Exam objectives call out protected cable distribution. So a protected distribution system encases network cabling within a carrier. It enables data to be securely transferred directly between two high security areas through an area of lower security. So we have a hardened carrier. This is where network cabling is run within metal conduit. All conduit connections are permanently welded or glued to prevent external access. To identify signs of tampering, regular visual inspections of the carrier should be conducted. An alarmed carrier. This is where welds or glue is used to secure a hardened carrier, are replaced with an electronic alarm system that can detect attempts to compromise the carrier and access the protected cable within it. So the key there being the electronic alarm system. That's the defining characteristic. And then we have continuously viewed carrier. This is where security guards continuously monitor the carrier to detect any intrusion attempt by attackers. Air gap. So we create air gaps between some systems that are used internally to separate confidential systems from standard systems. So the only way to insert or remove data from an air-gapped machine is by using removable media, such as a USB or CD-ROM drive. Hot and cold aisles. So the cold aisle is where the cold air enters and is contained. It faces the front of the servers, the rear of the servers face each other, and they push hot air out into the hot aisles. Hot air is allowed to escape through a vent or a chimney, or may be captured and channeled back to the HVAC unit, depending on the configuration. Hot and cold aisles need to be considered in data center design. This is the CSP's responsibility in the cloud, but if it's your data center, it's your problem. Vault is on the list of secure areas. This is generally where data can be encrypted and stored in the cloud, giving you an extra secure storage area. You'll also hear Vault used in solutions for storing passwords and secrets. A safe, so there are safes for the storage of laptops and tablets. We talked about fireproof safes for tape media a bit earlier as well. So I want to talk about the information lifecycle to get to the exam objective around secure data destruction. There's an important point to be made here. So data can be created by users, a user creating a file. It can be created by systems, so a system logs access. To ensure it's handled properly, it's important to ensure data is classified as soon as possible, and it's protected by adequate security controls in storage at rest based on its classification. Usage refers to any time a data is in use or in transit over a network. Archival is sometimes needed to comply with laws or regulations requiring data retention. And when data is no longer needed, it should be destroyed in such a way that it is not readable or recoverable. So I want to talk about the less secure data destruction methods. So there's erasing, which is performing a delete operation against a file, files, or media. Clearing or overwriting, which is preparing media for reuse and ensuring data cannot be recovered using traditional recovery tools. And then purging, which is a more intense form of clearing that prepares the media for reuse in less secure environments. Now, 3 things to know here. Number 1, the media is reusable with any of these methods. Data may be recoverable with forensic tools, and these 3 methods may be distractors in exam questions. Now, what you need to lock into your brain for the exam are the methods of secure data destruction. So let's talk about destroying media data. So this is data on media such as a hard drive or a DVD or CD-ROM. So there's degaussing. Degaussing creates a strong magnetic field that erases data on some media and destroys electronics. And then we have shredding. You can shred a metal hard drive into powder. Shredding is effective on DVD and CD-ROM as well. Pulverizing. You can use a hammer and smash a drive into pieces or drill through all the platters with a disk that has platters. In this case, the media is not reusable with any of these methods. This is secure media data destruction. The data is also not recoverable by any means in these cases as well. Destroying paper data. And these are listed in approximate order of efficacy. So it's destroying data on paper so it can't be stolen. So burning with fire, as in an incinerator on site or via a third-party vendor, providing a destruction certificate. Pulping. So if burning isn't available, pulping, which turns the data into paper mache effectively, is your best second option. And then shredding. If burning or pulping isn't possible, a cross-cut shredder would be best. It cuts it at 2 angles, so think vertically and horizontally, so chopping it into smaller pieces to make reassembly much more difficult than just a one-way shred. These methods are listed in order of effectiveness, though. And third parties may use different methods, but generally all will certify the task is complete. They'll give you some sort of certification notification. In section 2.8, we're asked to summarize the basics of cryptographic concepts. So the basics of cryptography. So let's start with digital signatures. So digital signatures are similar in concept to handwritten signatures on printed documents that identify individuals, but they provide more security benefits. It's an encrypted hash of a message encrypted with the sender's private key. In a signed email scenario, it provides 3 benefits. Authentication, so it positively identifies the sender of the email. ownership of a digital signature secret key is bound to a specific user. Non-repudiation, so the sender can't later deny sending the message. This is sometimes required with online transactions. And integrity, it provides assurances that the message has not been modified or corrupted, so recipients know that the message was not altered somehow in transit. These are the important basics for the Security Plus exam. I'm going to mention briefly the digital signature standard. So the DSS uses SHA-2 and SHA-3 message digest functions. It works in conjunction with one of 3 encryption algorithms, DSA, RSA, or elliptic curve DSA. The digital signature standard comes from NIST. It's documented at the URL here. I just wanted to drop this here for your edification if you want to dig into this a bit further. So key length. So some cipher suites are easier to crack than others. Larger keys tend to be more secure because there are more possible key combinations. Now, key stretching. This is a process used to take a key that may be weak and to make it stronger by making it longer and more random. A longer key has more combinations a brute force attack has to go through to crack. So since 2015, NIST recommends a minimum of 2048-bit key for RSA. This will change over time as computing power advances. Quantum computing will definitely impact this recommendation. So hashing versus encryption. So how is hashing different from encryption? So we talked about this briefly earlier. We're going to touch on it again here just in case. So encryption is a two-way function. What is encrypted can be decrypted with the proper key. Hashing, on the other hand, is a one-way function that scrambles plain text to produce a unique message digest. There's no way to reverse a hash if it's properly designed. Common uses of a hash include verification of digital signatures, generation of pseudo-random numbers, and integrity services. So file hash comparison, for example. Salting is also mentioned on the exam objective. So cryptographic salts come into play with your password. So attackers may use rainbow tables of pre-computed values to identify commonly used passwords. A salt is random data that's used as an additional input to a one-way function that hashes data, a password, or a passphrase. Adding salts to the passwords before hashing them reduces the effectiveness of rainbow table attacks. You're really relying on your identity provider, your identity platform, to implement cryptographic salts. Many of them do. Elliptic curve cryptography, or ECC. So ECC is a small, fast key that's used for encryption in small mobile devices. It was created because of the constraints that we have associated with the calculations that we use in asymmetric encryption. Curves in ECC are easier to calculate than the large primes typical in asymmetric encryption. But it's a small, fast key, so just to quantify that for you, here's a table of relative key sizes for ECC versus RSA, Diffie-Hellman, and El-Kamal. So algorithms for similar uses. So the smaller key makes ECC attractive for resource-constrained systems. You'll see there that it's a 160-bit ECC key. This chart's just for comparison only, just to show you that relative size difference. No need to memorize these details for the exam. So perfect forward secrecy. This is a feature of specific key agreement protocols that assures session keys will not be compromised if long-term secrets, think private key, is used in session key exchange and compromised later. So it indicates that a cryptographic system generates random public keys for each session, and it does not use a deterministic algorithm in the process. So given the same input, the algorithm will create a different public key, ensuring systems do not reuse keys. That's what it means to not be deterministic. It protects data on the transport layer that uses TLS protocols like OpenSSL. It uses more computing power than if you're using a single private key like on a web server, so it won't be a fit for all scenarios. But one of the key values of forward secrecy is that it protects past communication, reducing motivation for an attacker to compromise keys. So also on the exam objectives are symmetric versus asymmetric cryptography. So you'll want to know the difference. So symmetric cryptography relies on the use of a shared secret key. It lacks support for scalability, easy key distribution, and non-repudiation. It has a challenge in that respect. Asymmetric, or public key cryptography, uses public-private key pairs for communication between parties. It supports scalability, easy key distribution, and non-repudiation. Now I want to take you through an example with asymmetric cryptography. So in asymmetric, each party has their own public key and their own private key. So in this case, Franco sends a message to Maria requesting her public key. Maria sends her public key to Franco. Franco uses Maria's public key to encrypt the message and sends it to her. Maria uses her private key to decrypt the message. Maria is the only one, presumably, who can decrypt the message that was encrypted with her public key because it requires her private key to do so. And the reverse would be true if Maria were initiating this exchange with Franco. So taking this a step further, so with asymmetric key types, you have the public keys that are shared amongst the communicating parties and the private keys that are kept secret. And to encrypt a message, you use the recipient's public key. So Franco used Maria's public key. To decrypt the message, you use your own private key. So we saw Maria used her own private key to decrypt the message that was encrypted with her public key. Digital signatures. To sign a message, you use your own private key. To validate a signature, you use a sender's public key. So each party has both a private and public key in asymmetric cryptography. Now, to really bring together your understanding of these different cryptographic methods, let's talk about how these algorithm types are typically used. So asymmetric cryptography is typically used for bulk encryption, encrypting large amounts of data. An example of a symmetric algorithm is AES-256. Asymmetric cryptography is often used in distributing the symmetric algorithm's encryption key, because remember, it's a shared key, so asymmetric gives us a secure method for transmitting keys. It works well in identity authentication via digital signatures and certificates, so it's good for non-repudiation services and key agreements. So it really complements symmetric cryptography. The two work together in that respect, because symmetric cryptography, bulk encryption, is much faster with symmetric, but asymmetric allows us to securely transmit that key in a scalable fashion. Examples of asymmetric algorithms include RSA, DSS, and ECC, which we just talked about. Hash functions. Remember, hashing is a one-way function. Verification of digital signatures, so calculating the hash to ensure it's valid. Generation of pseudo-random numbers. Integrity services, so validating a file hash to ensure that it hasn't been altered, would be another example. So quantum and post-quantum show up in the exam objective. So quantum cryptography is the practice of harnessing the principles of quantum mechanics to improve security and to detect whether a third party is eavesdropping on communications. This leverages fundamental laws of physics, such as the observer effect, which states that it's impossible to identify the location of a particle without changing that particle. Now, quantum key distribution is the most common example of quantum cryptography. By transferring data using photons of light instead of bits, a confidential key transferred between two parties cannot be copied or intercepted secretly. And perhaps most relevant today is post-quantum cryptography. So post-quantum cryptography refers to cryptographic algorithms, usually public key algorithms, that are thought to be secure against an attack by a quantum computer. Post-quantum cryptography focuses on preparing for the era of quantum computing by updating existing mathematical-based algorithms and standards. So to put it a bit more simply, Post-quantum cryptography is the development of new kinds of cryptographic approaches that can be implemented using today's conventional computers, but that will be impervious, that will be resistant to attacks from tomorrow's quantum computers. So which algorithms are susceptible and which are resistant? Let's talk about that. So this slide here and the slide previous, I think, are the important basic concepts you need to know for the exam. I'm going to give you about 5 minutes of extra credit here to help you understand post-quantum cryptography concerns a bit better. And while I'm not a professional cryptographer, I have done quite a bit of research here, so I can, I think, adequately explain the concept for you simply pretty quickly. So how well do current encryption algorithms hold up to the power of quantum computing? So let's talk about symmetric and asymmetric. So shared key and public key cryptography. So remember, symmetric is for bulk encryption. It's fast encryption. And asymmetric handles our key exchange and our digital signatures. Remember how it works with symmetric. So symmetric holds up fairly well to quantum computing for the most part. Now quantum poses more immediate threats to asymmetric. So for symmetric cryptography, Grover's algorithm shows that a quantum computer speeds up attacks to effectively halve the key length, to cut the key length in half, that is to say. This would mean that a 256-bit key is as strong against a quantum computer as a 128-bit key is against a conventional computer. So doubling the key length from 128 to 256 does not make the key twice as strong. It makes it 2 to the 128th times as strong. So doubling the key length gives us a lot of extra bits, creating many more combinations to protect against brute force. So doubling the key length makes symmetric at 256 bits safe in the quantum scenario. Now asymmetric public key cryptography, Shor's algorithm can easily break all of the commonly used public key algorithms based on both factoring and discrete logarithm problems. So what this means is RSA is vulnerable. It means elliptic curve is vulnerable. However, lattice offers some resistance. Now, doubling the key length increases the difficulty to break an asymmetric algorithm by a factor of 8. That's not a sustainable advantage in the quantum scenario. So a quick note on lattice. I mentioned lattice offers some resistance. So based on different types of problem, the shortest vector problem and the closest vector problem is how lattice works. It's not working on large primes in the same way as other algorithms. So it potentially enables us to replace essentially all of our currently endangered schemes. And lattice-based cryptographic schemes make up the lion's share of scientific publications on post-quantum cryptography. Now I will say that research, selection, and standards development is ongoing. And NIST, the National Institute of Standards and Technology, initiated a competition, and they've worked down to around round 3, I believe. They're in the finals of choosing the algorithms that will win and be moved towards standards for quantum safe algorithms. And I believe 3 of the 5 finalists are lattice-based. So I believe it's going to be lattice-based cryptographic schemes that will sort of save the day in this respect. So what exactly is a lattice? I've mentioned lattice 3 or 4 times here. So a lattice is a 3-dimensional array of regularly spaced points. So this is just a simple diagram of what a lattice looks like. So that's all I'm going to say there. Let's move on to static versus ephemeral keys. So the 2 primary categories of asymmetrical keys are static and ephemeral. So static keys are semi-permanent and they stay the same over a long period of time is the key concept there. A certificate includes an embedded public key matched to a private key, and that key pair is valid for the lifetime of a certificate. Certificates have expiration dates and systems continue to use those keys until the certificate expires. 1 to 2 years is a common certificate lifetime for a client certificate. And a certification authority can validate a certificate static key with a certificate revocation list or using the online certificate status protocol. RSA uses static keys. Ephemeral keys have a very short lifetime and are recreated for each session. An ephemeral key pair includes a private ephemeral key and a public ephemeral key, and the systems use these key pairs for a single session and then discard them. Some versions of Diffie-Hellman use ephemeral keys. So modes of operation for block ciphers. So we have electronic codebook mode, which is the simplest and least secure mode. It processes 64-bit blocks. It encrypts the blocks with the chosen key. If the same block is encountered multiple times, the same encrypted block is produced, making it easy to break. There's cipher block chaining, where each block of unencrypted text is XORed. We talked about the XOR or exclusive OR earlier, with the block of cipher text immediately preceding. So the decryption process simply decrypts the ciphertext and reverses the XOR operation. And then there's counter, which uses an incrementing counter instead of a seed, so errors don't propagate. So blockchain is listed on your exam objectives, and blockchain was originally the technology that powered Bitcoin, but it has broader uses. So blockchain is a distributed public ledger that can be used to store financial, medical, or other transactions. Anyone is free to join and participate. It doesn't use intermediaries such as banks and financial institutions. And data is chained together with a block of data holding both the hash for that block and the hash of the preceding block. To create a new block on the chain, the computer that wishes to add the block solves a cryptographic puzzle and sends the solution to the other computers participating in that blockchain. This is known as proof of work. Cipher suites. So we have stream ciphers, and a stream cipher is a symmetric key cipher where plain text digits are combined with a pseudo-random cipher digit stream, a key stream it's called. In a stream cipher, essentially each plain text digit is encrypted one at a time with the corresponding digit of the key stream to give a digit of the cipher text stream. Now a block cipher, in contrast, is a method of encrypting text in which a cryptographic key and an algorithm are applied to a block of data. For example, 64 contiguous bits at once as a group rather than one bit at a time. Block ciphers are widely used today because it's a faster method of encryption than a stream cipher. Lightweight cryptography. This is an encryption method that features a small footprint and or low computational complexity. For the exam, elliptic curve cryptography, which is asymmetric, is the go-to for low power small devices, and AES is the symmetric algorithm for military. So just note those. And NIST is working on standards for lightweight cryptography. It's really important for embedded systems and other resource-constrained devices. And continuing through section 2.8, we're going to touch on some additional cryptographic concepts. We're going to touch on steganography, some limitations in the world of cryptography, and some common use cases. So let's start with steganography, which is where a computer, file, message, image, or video is concealed within another file, message, image, or video. So an attacker may hide info in this way to exfiltrate sensitive company data. It's a type of obfuscation. So homomorphic encryption allows users to run calculation on data while it is still encrypted. This allows data to be encrypted and outsourced to commercial cloud for processing because it can be processed while it's still encrypted. So common scenarios for specific cryptographic choices. So low power devices often use elliptic curve, ECC, for encryption as it uses a small key. IoT devices don't have the processing power for conventional encryption, generally speaking. Low latency means encryption and decryption should not take a long time. Specialized encryption hardware is a common answer in low latency scenarios. A VPN concentrator or an encryption accelerator card can improve efficiency in low latency scenarios. High resiliency. So in this case, we're using the most secure encryption algorithm practical to prevent the encryption key from being cracked by attackers. Device, application, or service compatibility may influence your decisions here. It's going to come down to supportability. Supporting confidentiality. So encryption should be implemented for exchange of any sensitive data and in a way that ensures only authorized parties can view. So for example, connecting remote offices via IPsec VPN gives us an encrypted tunnel between those two locations, ensuring the protection of that sensitive information. Supporting integrity. So two important scenarios for ensuring integrity would be ensuring file data hasn't been tampered with and that communications like an email are not altered in transit. So a file hash to check file integrity, a digital signature or DKIM for email. Supporting obfuscation. So obfuscation is commonly used in source code to ensure it cannot be read by anyone who steals it. So ROT13, XOR, or steganography can be used to obscure data. Supporting authentication. So a single factor username and password are not as secure as multi-factor usernames and passwords. MFA for user authentication, certificate-based authentication for devices. And supporting non-repudiation. So when you digitally sign an email with your private key, you cannot deny that it was you, as there is only one private key tied to you in that scenario. Non-repudiation is very important in any legally binding transaction. Limitations. So common scenarios for specific cryptographic choices. We're going to talk through some limitations. So there is speed. Application and hardware must be able to keep pace with the selected encryption. Size. If encrypting 16 bytes of data with a block cipher, the encrypted information is also 16 bytes. This overhead must be considered in resource planning. You need enough memory, storage, and network to support the result. Weak keys. So larger keys are generally stronger and thus more difficult to break. So you want to find balance between security, compatibility, and your compute capacity. Time. Encryption and hashing take time. Larger amounts of data and asymmetric encryption take more time than small amounts of data and symmetric encryption. Remember, symmetric is for bulk data encryption. So selections need to match time constraints in transactions. Longevity. Consider how long encryption algorithms you select can be used. So older algorithms will generally be retired sooner. That's only generally true, and then algorithms where weaknesses are found will also be accelerated toward retirement. Predictability. So cryptography relies on randomization. So random number generation that can't be easily predicted is crucial for any type of cryptography. Reuse. So using the same key is commonly seen in a number of encryption mechanisms, and if an attacker gains access to the key, they can decrypt data encrypted with it. And some IoT devices may not allow a key change, which means we have to store those keys very securely. Entropy. So this is a measure of the randomness or diversity of a data generating function. So data with full entropy is completely random with no meaningful patterns that can be discovered. Resource versus security constraints. So generally speaking, again, more secure the encryption used and the higher the key length, the more processing power and memory the server will need. So again, it just requires balance between your algorithms and your hardware selections. And congratulations, you have reached the end of Domain 2 of my Comptia Security Plus Exam Cram series. I hope you're getting value out of the series. Parts 3 through 5 are coming soon. We're currently about mid-January 2022. If you have any questions along the way, feel free to drop me a note here in the comments under the video description or reach out on LinkedIn. And until next time, take care and stay safe.